The stars aren't waiting for us, they're receding. Space itself is dragging them away, turning the night sky into a locked cell. Even with perfect engines and immortal crews, the universe hides a barrier no invention can cheat. So what is the real wall? Distance, time, energy, biology, or the expansion of reality itself? And why does it make going to the stars a beautiful impossibility? On the scale of stars, even our bravest velocity is almost motionless, and that is where the nightmare begins. A single light year is not a milestone. It is a regime where every shortcut becomes a bill. Tonight, the maps we grew up with will fail us because the universe is not arranged for travel, but for causality. We are used to thinking in routes and vehicles, in better engines and smarter navigation. Yet between one star and the next, the distance is not merely long. It is structured, layered with limits that multiply instead of add. In this film, we treat humanity's farthest probes as honest yardsticks, not heroic symbols. Their faint transmissions and slow, outward drift reveal a sobering scale, where nearby still means lifetimes. Then we meet the first gate, Relativity's accounting, where speed is purchased with energy that rises faster than the intuition. The closer you lean toward light, the more the universe resists, and the more your ship becomes an equation. But even if propulsion were perfect, the next constraints arrive quietly, in engineering details that refuse to stay small. Power must be stored, controlled, and dumped as heat, and thermodynamics demands receipts you cannot hide. And the emptiness between stars is not empty in the way our instincts imagine. At high speed, thin gas becomes a particle wind, and rare dust becomes impact physics, turning cruise into exposure. Beyond that, the story becomes intimate, even claustrophobic, because the vehicle is also a habitat. Bones, cells, minds, and closed ecologies do not simply endure time. They transform under it, and not always in ways we can reverse. Finally, we confront a limit that no material can reinforce and no algorithm can negotiate. Over interstellar durations, societies drift, purposes fracture, and destinations themselves keep moving, until travel is measured less in distance than in the stability of meaning. Across these chapters, we will follow a single thread through physics, biology, and history, asking what barrier remains when you remove every easy excuse. Not a missing invention, not a temporary obstacle, but a boundary written into how space-time keeps its promises. What emerges is not a single wall, but an architecture, one that compels every traveller to pay in energy, risk, and time all at once. And by the end, the question will feel less like, can we go? And more like this: what kind of beings could afford the universe we actually live in? Before we begin, let us know in the comments below where in the world you're watching from and what time it is there. Now, settle in for a journey. We begin with our fastest machines and the brutal arithmetic of the nearest stars, then climb through speed, energy, heat, and the hazards of the interstellar medium. From there, we enter the closed world of biology and deep time, until the final chapter gathers everything into one unyielding geometry. We begin with our fastest messengers, because they are the only honest yardsticks we possess. Voyager 1 and Voyager 2 left Earth in the 1970s and never stopped, coasting outward on momentum that still feels miraculous. New Horizons launched in 2006 and sprinted past Pluto with a clean, hard trajectory, its cameras briefly turning a distant world into a place. These probes are not prototypes of starships, and they are not rehearsals for crude voyages. They are the sharpest edge of what humanity has actually thrown into deep space: metal, silicon, and radio transmitters riding sunlight's fading reach. In archival footage, the launches look almost quaint: a tower of flame, a bright needle lifting into blue. Yet the real journey begins after the applause, when the spacecraft becomes a moving speck against a black field. The antennas keep talking, and the signal keeps weakening, spreading out as it travels. What returns to Earth is not a voice in the void, but a whisper measured in fractions of a watt. Deep Space Network dishes, white bowls against desert mountains, tilt and listen as if listening could shorten distance. After decades of flight, Voyager 1 is a little beyond the outer planet's domain in the way we usually tell the story. It has crossed the heliopause and entered interstellar space by one definition, marked by changes in plasma density and magnetic environment, yet it is still inside the Sun's gravitational neighbourhood in any practical sense. And gravity is the definition that matters for journeys. The Sun's influence stretches far beyond the planets into a vast halo of comets and slow debris. Even our farthest craft is still moving through home, still falling around the same star. That halo has a name that sounds almost mythical, the Oort cloud, and it is less a shell than a statistical fog. It may extend tens of thousands of astronomical units, perhaps a quarter of the way to the nearest stars. In that region, objects drift so slowly that a nudge from a passing star can reshape their orbits. The solar system, in other words, is not a neat set of rings. It is a deep gravitational well with long, dim outskirts. That is the first shock of scale, and it arrives quietly rather than dramatically. We talk about leaving the solar system as if it is a shoreline, a line you cross and then you are gone. In reality, it is an archipelago of distances nested inside larger distances, each one dwarfing the last. The boundary is not a wall. It is a gradient that keeps going long after the headlines end, long after the last planet is behind you. Distance is the real protagonist, and it speaks in units that resist intuition even when we recite them perfectly. 1 astronomical unit is the average Earth-to-Sun distance, a convenient ruler born from orbit and sunlight. It is about 150 million kilometers, a number we can almost picture because we live inside it. A light year is not a place. It is the distance light travels in 1 year, about 9.46 trillion kilometers, a unit built from speed rather than geography. Put those side by side and the mind slips, because the conversion is not emotionally linear. 1 light year is about 63,000 astronomical units, a ratio that turns the solar system into a dot on its own measuring tape. The outer planets sit tens of AU away, and the farthest probes are only a few hundred AU out. Alpha Centauri is about 4.37 light-years away, and it is not a single star, but a small family. That is roughly 276,000 AU, and the comparison is not flattering. On screen, you can draw the planets as marbles on a table, and still keep them recognizable. Add the Kuiper belt and the marbles become dust and the table becomes a field. Add the Oort cloud and the field becomes a county. Then place Alpha Centauri, and you need a different map entirely. One where the solar system is a pinprick, and the nearest neighbour is still far beyond the horizon. Voyager's speed is often quoted as heroic, around 17 kilometers per second relative to the Sun, and it is heroic by the standards of machines. At that pace, 1 astronomical unit takes a little over 100 days, and even that feels slow when you remember Earth crosses that distance in a year by simply orbiting. A light year takes about 17,600 years at Voyager speed, a span longer than agriculture and cities. Alpha Centauri would take around 77,000 years, longer than recorded human history. That is not a mission plan. That is geology, and geology does not care who launched you. There is another quiet detail hiding inside those numbers. Communication does not solve travel. Voyager's radio signal takes hours to reach Earth now, and that delay grows by minutes every week. At Alpha Centauri, even a perfect transmitter would speak with a 4.37-year pause. A conversation becomes a correspondence, and a correspondence becomes a kind of archaeology. New Horizons was faster at launch, roughly 16 kilometers per second after its Jupiter boost, and its flight to Pluto felt like a sprint. But it is still the same order of magnitude, still trapped in the arithmetic that governs all chemical propulsion. Chemical rockets can fling you out of the inner solar system quickly, especially with gravity assists that steal a little orbital energy from giant planets. They cannot make the gap between stars shrink. They can only change how quickly you realize how large it is. Ion propulsion changes the story only in shape, not in outcome, and that distinction matters. An ion engine sips propellant and throws it away at high exhaust velocity, using electricity to buy efficiency. It can accelerate gently for years, trading time and power for higher final speed, and the trajectory becomes a long, steady push rather than a single kick. In the best cases, it might reach dozens of kilometers per second, maybe a few hundred with extreme patience and power. Even then, a light year remains thousands of years. The numbers move, but the conclusion does not. So the conversation always turns to the same dream. What if we could go much faster? Not by a factor of 2, but by a factor of 10,000. What if we could reach a significant fraction of light speed? where the stars stop being distant ornaments and start being reachable targets. What if we could do a 0.1 c, 10% of c, the speed of light, without turning the ship into a bomb? At 0.1 c, a ship travels about 30,000 kilometers per second, fast enough to cross Earth in a heartbeat. That sounds like the threshold where the universe finally becomes small, where the map folds into something human. Alpha Centauri at 437 light-years becomes about 43.7 years of travel time in the Sun's frame, which is the clock Earth uses. If you include acceleration and deceleration, and you probably must, it becomes longer. If you want to arrive with control, it becomes longer again because arriving is a maneuver, not an ending. This is the 0.1 c illusion, and it is powerful because it is almost true. The number feels like liberation, but it is still a multi-decade crossing to the nearest star. It is a lifetime project even for a crew that never turns back, and even for a society that never loses interest. It is a mission that must survive politics, economics, and accidents for half a century. It is a mission that must remain coherent while Earth changes beyond recognition. Languages shift, institutions dissolve, and priorities mutate. There is also the physical meaning of 0.1 c, which the tidy number tends to hide. At that speed, the kinetic energy of each kilogram is enormous, and every additional ton of ship becomes an energy commitment. Small errors in navigation become large misses over light-year baselines, and course corrections cost real momentum. Even the dust between stars, microscopic grains, begins to look like incoming shrapnel when you meet it at tens of thousands of kilometers per second. And Alpha Centauri is the friendly case, the one we mention because it is close enough to feel like a neighbour. Most stars worth visiting are not the nearest, and the nearest star system is not necessarily the nearest habitable world. The nearest habitable world is not necessarily the one you can land on, because atmospheres, gravity and chemistry can be hostile. The nearest world you can land on is not necessarily the one you can live on, because living is more than standing on ground. Every step adds criteria, and each criterion tends to push the target farther away. Push outward, and the timescales stretch again, and they stretch in a way that changes what the word mission means. 10 light-years at 0.1 c is about a century, which is longer than most political orders survive. 100 light-years is a millennium, long enough for entire belief systems to rise and fall. The Milky Way is about 100,000 light-years across, and even 0.1 c turns it into a million-year ocean. The map of the galaxy does not become a travel brochure. It becomes a calendar that outlives civilizations, and calendars are indifferent to ambition. At this point, a familiar response appears, almost as a reflex. People say we just need better engines, and they point to history as evidence that limits are temporary. They say we should not be discouraged by early numbers, because early numbers once said heavier than air flight was impossible. They say technology always surprises us, and sometimes it does. The optimism has a history, and it has earned some respect. In the 20th century, propulsion improved quickly because we learned to handle energy more aggressively. We climbed from propellers to jets, from jets to rockets, and from rockets to probes that can leave the planetary region entirely. Each leap felt like a door opening, and each door made the next hallway visible. But interstellar distance is not just a longer hallway, it is a different kind of building. But this documentary is not hunting for a better engine, at least not yet. It is hunting for the barrier that survives even when you grant extraordinary technology, because that is where the real story lives. Imagine future humans with materials beyond our best alloys, strong under radiation and tolerant of heat. Imagine energy systems beyond our best reactors, compact enough to ride on a ship. Imagine navigation, automation and fabrication that feel like magic from our perspective. Even then, the same question returns. What is the non-negotiable wall built into the structure of reality? To find it, we have to treat distance as more than space between points, because space is not empty in the way our language suggests. It is filled with fields, particles, radiation and geometry, all of which have measurable consequences. It has rules about speed, energy and causality, rules that do not negotiate. It has a texture that becomes hostile when you move through it fast enough, like air becoming fire around a re-entering capsule. The stars look reachable because they are visible, and visibility is a psychological trap. They are bright, fixed, and emotionally close, and their light arrives nightly as if the distance is already conquered. Human imagination crosses light years in a thought, And a thought has no fuel tank, but physics charges interest on every shortcut, and the interest rate climbs with speed. Every extra percent of c costs disproportionately more, because energy does not scale gently near relativistic regimes. This is not a motivational problem, and it is important to say that plainly. It is not solved by bravery, or by a bigger budget, or by a single breakthrough that makes the hard parts vanish. It is a stack of constraints that reinforce each other, and the stack is what makes the barrier feel like a wall. If one constraint loosens, another tightens. If you solve one layer, the next layer becomes the real wall, waiting behind the first like a second door. We will build that stack in 4 pillars, because the barrier is not one thing. The first pillar is relativistic energy. To accelerate mass to a significant fraction of c requires enormous energy, and the requirement is not a matter of engineering taste. It is not just fuel, and it is not just efficiency. It is the energy to change momentum, and the energy you must later spend to slow down, because arriving fast is just crashing with a schedule. It is also the waste heat you must manage, and the engineering that must survive it. Radiators, structures, and systems that cannot melt or fracture. The second pillar is the interstellar environment, which sounds gentle until you quantify it. Between stars there is not nothing, even if the density is lower than the best vacuum we can make on Earth. There is thin gas, dust grains, cosmic rays, and high-energy particles, plus magnetic fields that thread through the medium. At low speed they are background, a sparse drizzle of impacts and radiation. At 0.1 c they become a sandblaster and a radiation storm, because kinetic energy turns rare collisions into violent ones. At higher fractions of c they become a lethal beam, and shielding becomes a mass problem that feeds back into energy. The third pillar is biology and closed ecosystems, because humans are not payloads like cameras. A multi-decade mission is not just a vehicle. It is a moving world that must recycle air, water, nutrients, and sanity, with no resupply and no rescue. It must handle reproduction or cryostasis or generational living, and each option carries its own technical and ethical weight. It must prevent small failures from compounding into collapse, because closed loops amplify mistakes. It must do this while the crew lives inside a machine that cannot stop and cannot easily be repaired with spare parts from home. The fourth pillar is the time architecture of civilizations, the least mechanical and often the most unforgiving. A mission that takes decades to millennia is not only hard technically, it is hard socially, because societies are not stable clocks. It must be funded and maintained across generations, and it must survive wars, economic crashes, and cultural shifts that can erase long projects overnight. It must remain meaningful to people who will never see the launch or the arrival, and who may not even share the same story about why it matters. These pillars are not independent, and the interlocks are where the trap closes. Energy determines speed, and speed determines environmental danger, which then demands shielding and redundancy. Shielding increases mass, and mass increases energy, and the loop tightens. Longer travel times increase biological complexity, and biological complexity increases mass, which again increases energy. Civilizational time affects what risks are acceptable, and what missions can be sustained, and what sacrifices can be justified without immediate reward. So Chapter 1 is a promise and a warning delivered in the same breath. The promise is that we will not dismiss interstellar travel with a shrug, because the dream deserves a serious trial. We will grant the best imaginable tools and see what still refuses to move, because that is how you locate a true limit. The warning is that the nearest shore is still an ocean away, and oceans do not care about desire. They care about mass, energy, and time. We can now state the central question with precision, and precision is a kind of respect. What is the fundamental barrier rooted in distance, relativity, environment, biology, and time that makes practical interstellar travel effectively impossible for humans? Not impossible in principle, because principles can be satisfied on paper. Impossible in practice, in the way a mountain range is passable but still stops armies, because the cost of passage exceeds what an army can carry. From here, we stop treating the stars as destinations and start treating the journey as a physical system. We will follow the cost curve as speed rises and watch how the universe enforces its interest rate, quietly and relentlessly. We will see why the wall is not at the edge of the solar system. It is embedded in the path between suns, in the space that looks empty until you try to cross it quickly. Next, we begin with the first pillar, because every other pillar depends on it. We begin with energy, and with the brutal fact that velocity is not just a number. It is a bill that must be paid twice, once to leave and once to arrive, and the universe always collects. Chapter 1 left us staring at the nearest stars like distant shorelights, steady and indifferent, as if the night itself were a map. The obvious response is speed, because distance feels like the protagonist, and velocity feels like the weapon we can still choose. But the universe does not treat speed like a dial you can keep turning, and it never promised that faster would remain merely harder. It treats speed like a contract, precise, enforceable, and written into the structure of space-time, so every extra fraction of light speed carries a rising price, paid in energy. Special relativity is the first hard gate, because it is not a technology limit that clever engineering can eventually bypass. It is a structural rule about space-time and causality, a rule confirmed every time particle accelerators push matter close to C and watch the numbers obey. Historically, that rule arrived as a correction to older instincts, because 19th century physics assumed time was universal and absolute. When Einstein reframed time as something woven with space, the speed limit stopped being a practical barrier and became a geometric one. The speed of light, c, is not just how fast photons move through vacuum, like bullets through air. It is how fast information can propagate through the universe, which means it is how fast cause can reach effect when nothing blocks the path. That matters because travel is not only motion across a backdrop, like a dot sliding on a screen. Travel is the movement of mass, energy, and information through a causal structure, where before and after must remain consistent for every observer. If you could exceed c, you could reorder cause and effect in some frames, turning a message into a warning that arrives before the event. Relativity blocks that by making c a limit built into the geometry, so the universe stays logically stitched together. Visually, imagine a grid drawn across space and time, like graph paper that extends into darkness, and then imagine the grid itself tightening as you accelerate. The faster you go, the more that grid dictates what paths are even allowed, light cones narrowing your options like rails. Those light cones are not just a metaphor, because they are the bookkeeping of space-time itself. They define which events can influence which other events, and at high speed your future becomes a narrower wedge, constrained by the same constant in every direction. So the dream becomes more specific, and in a way, more realistic. We do not need to beat light, because beating light triggers contradictions that physics refuses to host. We only need to approach it, close enough that the stars stop feeling like separate eras. We imagine 0.1 c, then 0.5, then 0.9 some, and we hope the costs scale like engineering, like stronger alloys and better turbines. We picture a future where the same basic idea simply improves, the way aircraft improve from canvas to carbon fibre. They do not. The hill steepens beneath your feet. Start with the simplest idea most of us learned first, because it still sets our intuition even when it stops being valid. In classical mechanics, kinetic energy is 1/2 mv squared, which means energy rises with the square of speed. Double the speed and the energy quadruples, and even that already sounds harsh when you imagine a ship rather than a baseball. Yet the curve is smooth, and it suggests that with enough fuel, you can always buy more speed in a predictable way. Relativity changes the curve as v becomes a significant fraction of c, and the change is not cosmetic. The relativistic kinetic energy is not 1/2 mv squared, because time and space themselves are part of the accounting, and the universe keeps perfect books. Instead, the kinetic energy becomes gamma minus 1 times mc squared, where gamma is 1 over the square root of 1 minus v squared over c squared. The equation looks like algebra, but it is really a warning label printed in symbols. Gamma is the price multiplier hidden inside the speed, and it is also the factor that shows up in time dilation and length contraction. At low speeds, gamma is almost 1, so the old formula works as a practical approximation, and everyday life stays Newtonian. Near light speed, gamma climbs fast, and it climbs without mercy, because the denominator is shrinking towards 0. The closer you get to c, the more each additional increment of speed demands a disproportionate increase in energy. The phrase everyone hears is that it takes infinite energy to reach c, and it often sounds like a dramatic slogan. It is not a mystical statement about engines, and it is not a moral claim about human ambition. It is a statement about the math of gamma. As V approaches C, the term 1 V2C2 approaches 0, and gamma diverges, rising without bound. In plain language, the universe refuses to let massive objects share the same kind of trajectory that light takes for free. Another way to say it is that your momentum keeps increasing even when your speed barely changes. You can pour in energy, and the ship will still get harder to accelerate because relativistic momentum scales with gamma as well. Conceptually, that means each additional increment of speed costs more than the last, like climbing a staircase where each step is taller than the one before. You can keep adding energy and keep getting smaller returns, because the structure of space-time is pushing back. You're not pushing on a free road where friction is the only enemy. You're pushing against the geometry that defines what speed even means, and the geometry does not negotiate. This is where the audience is allowed to hope, because the limit is at exactly c, not at 0.9 c or 0.99 c. If we stay below c, we can still have finite energy, and that sounds like a loophole worth exploiting. Then the bill arrives in the form of scale, because finite can still mean astronomical in the literal sense. Finite can still mean energies that rival the output of civilizations, not just engines. Consider what the numbers do even before we reach the extreme regime, because the punishment begins early. At 0.1 c, gamma is about 1.005, which sounds gentle, and in relativistic terms it is. The energy per kilogram is still enormous, but relativity has not yet fully tightened the screws. For 1 kilogram, the kinetic energy at 0.1 c is roughly 4.5 as 1014 joules, a number that already dwarfs familiar scales. To make that concrete, 4.5 x 1014 joules is on the order of 100 kilotons of TNT per kilogram, depending on which conversion you use. That is not a fuel tank problem, it is an infrastructure problem, because you must generate and control it. Picture that energy as a bright invisible reservoir, stored not as heat, not as electricity, but as sheer motion. If that kilogram hits anything, even a grain of dust, the release is not cinematic fire, but physics, abrupt and absolute. At 0.5 c, gamma is about 1.155, and the kinetic energy is about 0.145 all c squared. That is not a small correction to the classical estimate, and it is not a rounding error that better spreadsheets can hide. For 1 kilogram, 0.155 meta C2 is about 1.4 as 1016 joules, which is tens of megatons of TNT equivalent. 1 kilogram moving at half-light speed carries the energy of a large nuclear arsenal, stored not in chemistry but in motion. At 0.9 c, gamma is about 2.294, and the kinetic energy is about 1.294 mass c squared. You're now spending more than the rest energy of the mass in pure motion, which is a sentence that should feel unsettling. Because mc squared is the energy locked inside matter itself, the famous E-like mc2 that became shorthand for the 20th century. When kinetic energy exceeds mc2, you are investing more energy in the ship's motion than is stored in its atoms at rest. At 0.99 c, gamma is about 7.09, and the kinetic energy is about 6.09 c squared, which means the ship's motion represents multiple times its own mass energy. The decimal places start behaving like a trapdoor, because each one hides a multiplier. At 0.999 c, gamma is about 22.4, and the kinetic energy is about 21.4 c squared. Each extra 9 in the decimal place is a new tier of expense, and the tiers do not come with discounts. These are not abstract symbols floating in a vacuum, because mc2 is a real conversion rate between mass and energy. 1 kilogram has a rest energy of about 9 x 1016 joules, which is roughly the energy released by burning billions of kilograms of fuel. Now picture a ship that is not 1 kilogram but a vessel with structure, shielding, life support, redundancy, and a payload worth sending. Even a small interstellar craft might be tens of tons, and a crude habitat could be thousands. The numbers scale linearly with mass, which makes them brutally honest. If 1 kilogram at 0.5 c is tens of megatons of TNT, then 100 tons at 0.5 c is a planetary scale energy commitment, and it must be paid twice if you want to stop. Now compare the intuitive milestones people like to cite, because our language hides the real curve. Going from 0.1 c to 0.5 c is not 5 times harder, and it is not 5 times more fuel in any reasonable sense. It is vastly more expensive in energy per kilogram. Going from 0.5C to 0.9C is not a modest upgrade, like swapping an engine block. It is another jump, and the jump is paid in orders of magnitude because gamma is not linear and it does not care about our preferences. This is the first tension beat, and it is a visual one as much as a mathematical one. The stars look close if you can reach high fractions of C, and the black between them looks like empty runway. Relativity allows you to try, and then it demands that you pay. In the mind's eye, you can show a simple graph, with speed on the horizontal axis and energy on the vertical, and the curve rising gently at first. Then, near the right edge, the curve turns upward like a cliff face, and the labels stop fitting on the screen. The next temptation is time dilation, because it sounds like a cheat code hidden inside the rules. If time slows down for the travellers, then even long distances might feel short, and relativity itself seems to offer the escape hatch. Time dilation is real, and it is one of the most tested predictions in physics, not a speculative idea. Muons created in Earth's upper atmosphere survive longer when moving fast, and atomic clocks flown on aircraft tick differently than their twins on the ground. Those experiments are not just trivia, because they show time dilation is not psychological. It is a measurable change in proper time, the time a clock experiences along its path through space-time, no matter what the clock is made of. A fast-moving clock ticks slower relative to a stationary observer, and the factor is the same gamma that multiplies kinetic energy. If you travel at high gamma, you can cross light years while experiencing less time on board because your proper time is compressed. That is the seductive part, and it deserves the cinematic treatment. Imagine a ship's interior lit by soft panels, the crew watching a calendar that barely advances, while outside the starfield slides and shifts in a forward collimated tunnel of light. The ship's crew could, in principle, see the galaxy within a human lifetime of proper time, hopping between regions that would otherwise be separated by generations. The universe seems to hand you a way around the tyranny of distance, and it feels almost like mercy. Then the second tension beat lands, because relativity gives with one hand and takes with the other. Time dilation does not reduce the energy cost, and it does not reduce the momentum change required. It does not reduce the hazards of moving through interstellar space at that speed. It only changes whose clock suffers, and that distinction is the heart of the story. From Earth's frame, the trip still takes years or centuries, because the distance is still there and the ship is still below sea. The outside universe still waits, and it still changes while you're gone, with or without your consent. Your home world still ages, your institutions still decay, and your mission still has to remain coherent across that external time. Even if the crew experiences 5 years, Earth might experience 50, and the difference is not a philosophical curiosity. It affects politics, funding, language drift, and the simple fact that everyone you left behind becomes history. From the ship's frame, you can compress the subjective duration, but you cannot compress the physics bill. In fact, high gamma is itself a measure of how expensive the trip is, because the same gamma that gives you time dilation multiplies your kinetic energy. To get dramatic time dilation, you need dramatic gamma, and gamma is not cheap. Gamma of 2 is already 0.866C, which is far beyond anything humans have ever propelled in bulk. Gamma of 10 is about 0.95C, where the energy curve is already nearly vertical. Gamma of 100 is about 0.9995C, and at that point the ship is living inside the extreme regime, where tiny changes in speed demand civilization-level energy. The dream becomes a question. What kind of society can afford to move a habitat like a particle beam? Time dilation also comes with a second hidden cost that is not optional, because the universe is not empty in the way our metaphors suggest. At high speed, the interstellar medium becomes a radiation source in your forward direction, and the ship becomes its own particle experiment. Interstellar space is thin, but it is not nothing, with roughly 1 atom per cubic centimetre in many regions and more in others. At ordinary speeds, those atoms are irrelevant, like a few dust motes in a cathedral. At relativistic speeds, they become impacts with particle accelerator energies. Sparse hydrogen atoms become high-energy collisions that can generate showers of secondary particles when they strike a shield. Each impact is small, but the flux adds up over light years, and at high gamma the energy per impact is multiplied into the dangerous range. Background photons also change character, because light is not just visible starlight, It is the cosmic microwave background filling space at 2.7 Kelvin. In the ship's frame, those microwaves are blue shifted forward into higher frequencies, and the forward sky hardens. At sufficiently high gamma, what was harmless microwave radiation becomes infrared, then visible, then ultraviolet, and eventually X-rays in the forward direction. The ship's nose becomes a place where the universe's faint background turns into a headwind of radiation, so the very speeds that make time dilation attractive also intensify shielding requirements, and shielding is never massless. Shielding adds mass increases energy, and the loop tightens until the mission starts to feel like an equation that eats its own tail. Visually, you can show the ship's forward shield glowing with false colour, a simulation of particle tracks and radiation cones. The stars ahead compress into a bright patch due to relativistic aberration, while behind the ship the sky dims, as if the universe is being left behind. At this point, a viewer might still say the problem is only fuel efficiency, because we are trained to believe better engines solve hard travel. If we had a perfect engine, we could pay the energy and be done, and all this would become a matter of industrial scale. That is where the rocket equation enters, because it is not about engine quality or cleverness. It is about carrying your own reaction mass, and it punishes you even if your engine is flawless, because the punishment is geometric. The rocket equation is the tyranny behind every propulsion system that throws mass out the back, whether it is hot gas, ions, plasma, or something more exotic. Delta V equals exhaust velocity times the natural log of initial mass over final mass, and that logarithm is the trap. It is worth pausing on what the logarithm means, because it hides its cruelty behind a familiar function. Each time you want more delta V, you do not add a little more propellant. You increase the starting mass that must be accelerated from the very beginning. Delta V is the total change in velocity you need, not the cruising speed alone, and it is easy to underestimate. It includes acceleration, course corrections, and crucially, deceleration, because a mission that cannot stop is not a mission that can arrive. The equation says that for a given exhaust velocity, each additional unit of delta V requires a multiplicative increase in mass ratio. You do not add fuel linearly, like topping off a tank. You multiply the ship because the fuel must accelerate itself along with everything else. This is where the documentary has to be honest about the difference between energy and propellant. Energy is the physics bill, the unavoidable cost of changing momentum at relativistic speeds. Propellant is the engineering method for paying it, and the rocket equation punishes the method. There is also a historical echo here, because the rocket equation is older than spaceflight itself, derived by Tsiolkovsky in the early 20th century. Long before humans reached orbit, the math was already warning that rockets are exponential machines, and exponential machines are unforgiving. Chemical rockets have exhaust velocities of a few kilometers per second, which is why they are hopeless for relativistic travel. Even to reach tens of kilometers per second, chemical stages become absurdly large, and the payload fraction collapses into a rounding error. Nuclear thermal improves exhaust velocity, but not by orders of magnitude, because it is still limited by material temperatures and molecular mass. Electric propulsion can reach tens of kilometers per second of exhaust velocity, sometimes more, but it requires huge power and long burn times. To reach 0.1 C, your exhaust velocity must be a significant fraction of C, or your mass ratio becomes grotesque. If exhaust velocity is much lower than your target delta V, the logarithm demands exponential propellant, and exponential is a word that should make engineers flinch. Even if you imagine an engine with exhaust velocity near C, the rocket equation still bites, because the logarithm never goes away. You still need propellant mass comparable to payload mass for large delta V, and that is before you add shielding, habitat, and redundancy. In visuals, you can build a mass ratio ladder, where each rung is a new stage of propellant, and the payload shrinks as the stack grows. The ladder climbs quickly, and then it becomes a tower, and then it becomes a number you can only write in scientific notation. Now add the part most casual plans forget, because it is psychologically easy to ignore. You have to slow down. Deceleration is the hidden half of the journey, and it is not a footnote you can handle later. Arriving at another star at 0.1 C is not arrival. It is a flyby that lasts hours or days, followed by departure into darkness. If the mission goal is exploration, sampling, or settlement, you need to brake, and braking is not optional unless you accept a one-shot glimpse. Braking requires delta V comparable to your acceleration delta V, which roughly doubles the propulsion requirement. Doubling delta V does not double propellant, and this is where the rocket equation becomes a narrative villain. The equation turns it into a multiplication of mass ratio, because the ship must carry the propellant to carry the propellant that will later slow the ship. This is the third tension beat, and it is one audiences feel in their gut once it is stated clearly. The audience can accept a hard push to get moving, because that feels like the heroic part. They often forget that stopping is equally expensive, and the universe charges you at both ends, so we can sketch a simple budget, not as a final design but as a reality check. A one-way 0.1c mission needs about 0.1c of delta V, plus margins for navigation and error. A rendezvous mission needs about 0.2c of delta V, plus margins, because you must match velocities. Any realistic plan adds more for course corrections and contingencies, because interstellar space is not a perfectly predictable corridor. Small errors compound over years, and the ability to correct them is part of what makes a mission survivable rather than merely launched. Even if we ignore the rocket equation and speak only in energy, the doubling still matters, because energy is not just spent on the way up. Kinetic energy scales with gamma, and you must remove that energy to stop, which means you must have a place for it to go. You can radiate it away, dump it into propellant, or exchange it with an external medium, but you cannot pretend it disappears. In physics, stopping is not the absence of motion, it is the active transfer of momentum and energy to something else. This is also where waste heat becomes a quiet but relentless constraint, because any real propulsion system produces heat that must be rejected. In space, heat leaves primarily by radiation, which means large radiators, careful thermal design, and time, none of which become easier at high speed. At this point, the hopeful viewer reaches for speculative drives, because the mind wants a door that the math cannot close. They say we will invent something that does not need propellant, or something that makes the rocket equation irrelevant. They say we will use antimatter, fusion, beamed sails, or some exotic field. Some of those ideas can change the mechanism, and that is worth acknowledging without surrendering the accounting. They can move the propellant off the ship, or change how momentum is exchanged, or raise exhaust velocity toward the theoretical ceiling. But none of them erase the bookkeeping of momentum change, because momentum is conserved as stubbornly as causality. To change the ship's velocity by a given amount, you must exchange a corresponding momentum with something else, whether that something is propellant, photons, or an external beam. The energy associated with that exchange is set by relativity, and the closer you get to C, the harsher that setting becomes. You can choose where the energy is generated, and you can choose how it is delivered, but you do not get to choose whether it is required. Beamed sails still require the beam source to deliver enormous energy, and that source must be built, powered, and aimed with extraordinary precision over astronomical distances. The sail may be light, but the infrastructure behind it is heavy in every sense. Antimatter still requires producing and storing energy-dense fuel with extreme losses and hazards, because antimatter is not a substance you mine. It is manufactured at a cost, and it must be held away from normal matter with fields that cannot fail. Fusion still demands reaction mass and high exhaust velocity, plus a reactor that survives for decades in a harsh radiation environment. The concept is powerful, but the engineering is not a footnote, because a long-duration relativistic mission is a stress test of everything. Even a perfect engine cannot make the kinetic energy requirement vanish, because the requirement is not about inefficiency. It can only approach the theoretical minimum for a given mission profile, and the minimum is still enormous once the mission is measured in light years. This is the chapter's core reframing, and it is meant to land like a quiet realization rather than a scolding. Interstellar travel is not primarily an engine problem, as if we simply need a better nozzle. It is an energy and momentum problem enforced by space-time itself. Now we connect back to the central question, because the story is not only about equations, it is about what they imply. If the universe is an ocean of stars, relativity is the current that runs against you, and it never stops flowing. It does not forbid motion, and it does not mock the dream of reaching other suns. It makes fast motion expensive in a way that compounds, and compounding costs are what separate difficult from transformative. The compounding is the real barrier, and it appears in multiple forms that reinforce each other. Higher speed demands higher energy demands more power and more mass handling, and more mass demands more energy again, because you must accelerate what you bring. Higher speed also increases environmental hazards, which demand shielding, and shielding adds mass, which raises the energy requirement once more. The loop is not a metaphor, it is the architecture of propulsion, and it is why optimistic sketches often collapse under their own assumptions. Time dilation tempts you with a personal escape, but it does not rescue the mission from external time, and it does not rescue you from radiation and impacts. It does not rescue you from the energy curve, because the curve is the same curve that creates the dilation. The rocket equation turns the energy problem into a mass problem, and the mass problem feeds back into the energy problem, tightening the spiral. The ship becomes heavier, the required delta V becomes harder to pay, and the design becomes more fragile as complexity rises. So the speed trap is not that you cannot go fast, because physics does allow astonishing velocities below C. The trap is that every step toward fast makes the rest of the mission heavier, hotter, and more fragile, and fragility is the enemy of long voyages. We can now state the price tag in plain terms, without hiding behind symbols. To approach light speed, you must spend energy comparable to the energy content of the ship's mass, and you must then spend comparable energy again to stop, unless you accept a flyby. You must manage waste heat and radiation while doing it, and you must do it for years, not seconds, because interstellar distances are patient. You must also build systems that remain reliable across long durations, because a breakdown halfway is not a roadside inconvenience. And you must do all of this in a universe that does not provide convenient breaks. Space is thin, which sounds helpful until you need something to push against, because emptiness is a poor partner for momentum exchange. The emptiness that makes travel possible also makes stopping difficult, and that is an irony built into the setting. In a dense medium you could brake by drag, but drag would also destroy you at high speed. In a thin medium you survive, but you must bring your own way to shed velocity. This is where the chapter ends on a controlled disappointment, because the goal is not to extinguish wonder. The audience is allowed to keep the dream, but not the easy version, and not the version where speed is a simple slider. Relativity does not slam the door, and it does not declare interstellar travel impossible. It posts the price list, and the price list is written in gamma in delta V and in the stubborn conservation laws that have never once blinked. From here, we stop treating speed as a simple solution and start treating it as a cascading liability. The next layer of the barrier is what that speed does to the space between stars, because the void is not empty when you hit it fast. Because once you pay for velocity, the interstellar medium sends its own invoice, and it is not negotiable. And it is written in radiation, impacts, and erosion that no clever engine can talk its way around. Chapter 2 posted the price list for speed, written in gamma and delta V, and it treated energy like a line item. Chapter 3 asks a harsher question: where does that energy live, and how does a ship survive using it? Interstellar travel fails quietly when you stop talking about velocity and start talking about storage, plumbing, and heat. A starship is not a formula. It is tanks, reactors, radiators, magnets, and materials that must work for decades. The numbers on paper are obedient, but hardware has moods: thermal gradients, vibration, fatigue, corrosion, and the slow drift of calibration. In the diagrams, engines are clean cones and glowing plumes, but real hardware is cluttered and stubborn. Pipes frost, valves stick, coils quench, and sensors drift, and none of that cares about your destination. The camera would not linger on the heroic nozzle, but on the cramped service corridor. Wiring harnesses bundled like vines, insulation blankets stitched and patched, warning labels faded by radiation. When the mission lasts longer than a human career, reliability becomes a physical requirement, not a management slogan. Redundancy is not just extra parts, because extra parts add mass and heat and failure modes of their own. Even lubrication becomes a story because oils crack under radiation and bearings pit under micro-vibration that never stops. Energy density is the first ladder every plane must climb, because it decides what fraction of the ship is deadweight. It is measured in joules per kilogram, but it is felt as volume, shielding thickness, and radiator span. A design that looks elegant at the blackboard becomes grotesque when the energy must be carried as matter. The ship's silhouette changes as you add what the equations politely omit: structure, containment, and the margins that keep a system alive. Chemical energy sits near the bottom, measured in tens of megajoules per kilogram for the best propellants. That number sounds large until you compare it to orbital mechanics, because escaping a planet already spends much of it. It is enough for launch and orbit, not enough for light-year missions. The visual is almost cruel. a towering chemical stage that empties itself in minutes, leaving only a small payload and a long, indifferent night. Chemical rockets also pay a second tax that spreadsheets hide. Their energy is locked into hot exhaust at limited temperature. Combustion chambers and nozzles cannot exceed material limits for long, so exhaust velocity stays in the few kilometers per second range. The rocket equation then turns ambition into arithmetic, and arithmetic into despair. Every extra kilometer per second demands more propellant, and more propellant demands more tank, and more tank demands more propellant again. Fission climbs higher, roughly millions of times denser than chemical, when counted as nuclear binding energy. In principle, splitting heavy nuclei releases about 1,000,000 times more energy per kilogram than burning molecules. In practice, the reactor is not just fuel. It is a pressure vessel, control system, shielding, and a heat engine. The fuel may be dense, yet the machine around it grows heavy, because the machine must survive its own radiation. The historical lesson is sobering, because we have already tried to ride fission into deep space. Project Rover and Nerva in the 1960s built nuclear thermal rockets that heated hydrogen with a reactor core. They worked on test stands, roaring in the Nevada desert while instruments watched temperatures climb toward the limits. The dream was simple: use nuclear heat to push propellant faster than chemistry can manage, and cut the mass ratio that strangles missions. They did work, but politics, cost, and fear of accidents ended the program before flight. The era that built them also feared them. Public concern after atmospheric testing, shifting budgets, and the risk of a launch failure scattering radioactive material. Those engines became artifacts of a path not taken, filmed in grainy footage where the plume is bright and the surrounding desert looks too quiet. A fission rocket still faces temperature limits, heavy shielding, and waste heat that must be rejected into space. You can make the propellant hotter, but the fuel elements erode and crack under thermal shock. You can add shielding, but every kilogram of shielding is another kilogram you must accelerate and then decelerate. The shielding is also not uniform because you can shadow shield the crew while leaving other directions exposed, yet that geometry complicates the ship's layout. Fission also runs into mission architecture limits that are easy to miss when you only quote specific impulse. A high-thrust fission rocket wants hot propellant and robust nozzles, which drives mass and complexity. A low-thrust electric system wants huge electrical power and long burn times, which stretches the mission and increases exposure. The ship either burns like a torch for minutes or whispers for years, and both choices come with consequences. Electric propulsion looks gentle in animation, a blue thread against black, but its math is relentless. High exhaust velocity saves propellant, yet power sets thrust, and thrust sets trip time. If you cannot push hard, you spend years spiraling outward while radiation and micrometeoroids keep rolling the dice. The visuals are patient and unsettling. A spacecraft tracing a widening spiral, the sun shrinking behind it, the engines glow steady and small. Fusion climbs again, promising a larger fraction of mass converted into energy, and that is why it haunts interstellar proposals. The best fusion reactions can release energy per kilogram that dwarfs fission fuel mass, but only if you can actually burn it efficiently. The phrase fusion torch ship implies a compact star in a box that never misfires. It also implies a power density that would make any terrestrial plant look like a candle. Fusion's appeal is simple, and it is almost poetic. If you can fuse light nuclei efficiently, the energy per unit mass is enormous, and the reaction products can be fast. You can in principle push exhaust velocities far beyond chemical limits, and reduce the mass ratio that destroys conventional rockets. On a chart, the curve bends in your favour, and for a moment interstellar travel looks like engineering instead of fantasy. Fusion's limit is also simple, and it is not a matter of optimism. We have not demonstrated a controlled net power fusion reactor on Earth, let alone one that is compact, lightweight, and flight reliable. The gap is not a missing bolt, it is missing physics and missing engineering at scale. Even the best experiments are still learning how to keep a plasma calm when it wants to writhe. Ignition is the first wall, and it is not negotiable. A fusion plasma must be hot enough, dense enough, and confined long enough to let nuclei collide and fuse. The Lawson criterion is not a suggestion. It is the minimum condition for a reactor that does not consume more energy than it produces. In plain terms, the plasma must stay together long enough for enough reactions to happen, before it cools and falls apart. Those three variables, temperature, density, and confinement time, can trade with one another, but none can be ignored. If density is low, particles rarely meet, so you need longer confinement and higher temperature. If confinement is short, you must compensate with higher density and driver power, and that driver power becomes heat. The trade space is not generous, because every lever you pull pushes stress into another subsystem. Confinement is the second wall, and it is where plasmas reveal their personality. Magnetic confinement tries to hold plasma with fields, but plasmas leak, twist, and generate instabilities that feed on tiny errors. Inertial confinement tries to crush fuel pellets, but repetition rates and driver efficiency remain far from propulsion needs. Both approaches can produce flashes of success, yet propulsion requires endurance, hours, months, and years of controlled burning. In a tokamak, the plasma is a living current loop, and it pushes back on the magnets that restrain it. Kink modes, tearing modes, and edge-localized bursts can dump energy into the wall in milliseconds. On Earth, you can shut down, repair, and try again, but a starship cannot call a technician. The visuals here are clinical: magnetic coils like rib bones around a bright, unstable ring, sensors blinking as the plasma jitters. Inertial confinement looks cleaner in concept because the fuel is separate from the chamber. A pellet implodes, fusion flashes, and the chamber resets, and the cycle repeats like a heartbeat. Yet propulsion would need that heartbeat many times per second. With exquisite pellet injection and near-perfect driver efficiency, the chamber would be a drum being struck continuously, and every strike would shake, heat, and erode the walls. A Starship reactor cannot be a single laboratory shot, and it cannot be a fragile experiment. It must be a machine that runs continuously, throttles safely, and survives vibration and radiation. It must do this while also being the engine, not merely a power plant. That means the reactor's output must be shaped into momentum, not just captured as electricity and admired on a meter. That distinction matters, because a power plant can be heavy and still useful, while an engine must throw momentum. If the reactor produces electricity, you must convert it into thrust with turbines, generators, power electronics, and thrusters. Each conversion step sheds efficiency, and each inefficiency becomes waste heat. The ship becomes a chain of compromises, where every interface is both a feature and a failure point. Fuel cycles decide whether fusion is even plausible for a ship, because the reaction choice sets radiation, temperature, and engineering burden. Deuterium, tritium is the easiest to ignite, which is why most near-term designs focus there. It also produces a flood of fast neutrons that punish every surrounding material. The fuel is attractive because it lights readily, and terrifying because it lights everything else as well. Neutrons are the hidden tax on DT fusion, and they are indifferent to your magnetic fields. They carry most of the energy, but they cannot be steered, focused, or reflected like charged particles. They slam into structures, embrittle metals, activate components, and turn the engine into a long-term radiation source. In visuals, the neutron flux is invisible, yet its effects are not. Darkened insulators, cracked ceramics, and metal surfaces that look sandblasted on an atomic scale. That damage is not cosmetic, and it is not slow. Neutron bombardment displaces atoms in crystal lattices, swelling and weakening alloys, while transmutation changes the material itself. Insulators darken, lubricants crack, and electronics suffer single-event upsets that become permanent failures. Even superconducting magnets, which promise strong fields with low losses, can be driven normal by radiation heating. One quench in the wrong moment can cascade into catastrophe, so DT fusion forces thick shielding, frequent replacement, or exotic materials that must be manufactured and maintained in flight. Every kilogram of shielding is another kilogram you must accelerate and then decelerate, and that mass multiplies through the mission. The engine begins to resemble a moving fortress built around a fire. The ship's center is not a cockpit or a habitat, but a carefully managed zone of violence. He3 fusion reduces neutron production and looks cleaner for propulsion, because more energy stays in charged particles. Charged products can, in principle, be guided by magnetic nozzles into directed exhaust. Yet the reaction demands higher temperatures and rarer fuel, and those demands echo through the entire design. Higher temperature means harsher plasma behavior, stronger fields, and stricter tolerances, because the margins shrink as power density rises. Helium-3 is not a convenient resource on Earth, and it does not appear in tanks waiting for you. It exists in trace amounts from radioactive decay and in the solar wind, and harvesting it at scale is a project measured in mines and megawatts. The fuel problem becomes a supply chain problem stretched across worlds. Even optimistic scenarios talk about lunar regolith processing or gas giant skimming, industrial operations that must run for years before a single ship departs. Proton, boron fusion, looks even cleaner, because it can be mostly aneutronic in ideal conditions. Its products are alpha particles, which are charged and in principle steerable into thrust. It also requires temperatures and confinement far beyond current capabilities, and side reactions still generate neutrons and hard radiation. The promise is a cleaner exhaust, but the price is an even more demanding reactor, one that must be hotter than any practical container wants to allow. Even if you solve ignition and confinement, you still face power handling, and that is where cinematic language collides with metal. A torch ship implies terawatts to petawatts of power, flowing through a compact engine. That power must be converted into directed exhaust without melting the machine. At those levels, even tiny inefficiencies become kilotons of heat, and even small asymmetries become destructive forces. In concept art, the exhaust is a neat spear of light, but real exhaust is a plasma with turbulence and boundary layers. Magnetic nozzles must hold that plasma away from walls, and any contact becomes erosion at absurd rates. The engine must also survive its own electromagnetic forces, because high currents produce crushing stresses. The coils are not just conductors, they are structural members, fighting to keep their shape while fields try to tear them apart. The next wall is heat, because no engine is perfectly efficient, and because structure always absorbs something. Some fraction of energy becomes waste heat in coils, power electronics shielding, and exhaust handling, even if the reaction itself is clean. In space, you cannot dump heat into air or water. You can only radiate it. That single fact turns into architecture, because it dictates what the ship must look like from far away. Radiators are not optional accessories, and they are not a detail you add after the engine is chosen. They are the physical expression of thermodynamics, drawn in metal and carbon panels. If your ship runs at high power for years, its radiator area becomes a major fraction of the vehicle's mass and cross-section. The visuals widen, thin dark panels unfolding like wings, latticed with heat pipes and pumped loops, trembling slightly as the ship accelerates. The Stefan, Boltzmann law sets the scaling, and it is brutally simple. Radiated power equals emissivity times sigma, times area times temperature to the fourth. If you want to reject more heat, you need higher temperature, larger area, or both. And because area is literal surface, the ship's thermal design becomes visible, an object shaped by the need to glow. Higher temperature sounds like a shortcut because the fourth power looks like magic, but materials set limits. Radiators must survive micrometeoroids, radiation, and thermal cycling, and they must keep their emissivity. They must also avoid becoming so hot that they glow intensely and waste energy as visible light. A radiator that runs too hot is not only stressed, it is also throwing away useful power in wavelengths you did not intend. A hot radiator is not just a cooler, it is also a beacon. In infrared it can shine like a small star, and that visibility matters for any ship that cares about detection. The glow is also a reminder that power has consequences, because every watt you use must eventually leave as photons. The ship can hide its thrust, perhaps, but it cannot hide its entropy, because entropy is what radiators are for. So more power means more glowing surface area, spread like wings or panels, and those panels have to be supported. That surface area is fragile and hard to protect, because armour adds mass and mass adds heat again. It also increases collision risk at high speed, because the ship presents more target to the interstellar medium. A radiator is a sail in the worst sense, something large that you must keep intact while flying through a sparse but unforgiving environment. Life support adds its own steady heat load, and it does not politely scale down when the engine throttles. A crewed ship is a habitat with people, machines, farms and recycling systems, and every process ends as heat. Even modest electrical power becomes waste heat that must be radiated, and the radiator requirement never takes a day off. The visuals tighten to interior shots, condensation traps, air scrubbers, pumps, and fans, all of them turning energy into warmth that must go somewhere. This is where the tension rises, because the constraints stack rather than substitute. Relativity demanded huge energy to change velocity, and thermodynamics demands huge surfaces to dispose of the byproducts. The ship becomes not just powerful, but thermally enormous, an engine wrapped in a glowing sail of its own waste. And the question becomes uncomfortable. How fast can you go before your cooling system becomes the dominant structure? Antimatter appears as the clean escape from fusion complexity, and the temptation is understandable. It offers the highest energy density imaginable, and it can in principle drive photon rockets or heat propellant to extreme exhaust velocities. It also concentrates danger into the smallest possible package. The visuals become minimal and ominous. A small containment module, isolated at the end of a long truss, surrounded by sensors and redundant power feeds. Antimatter is not a fuel you discover, and it is not a fuel you refine from ore. It is a fuel you manufacture, particle by particle, using enormous energy and delicate machinery. In modern accelerators, we make nanograms at best, and the energy efficiency is catastrophically low by any practical standard. Even if future methods improve, the thermodynamic reality remains. Creating antimatter is an expensive way to store energy, not a cheap way to find it. Even in an optimistic future, producing kilograms of antimatter implies industrial power on the scale of nations, sustained for long periods. It implies dedicated solar collectors or reactors whose primary output is not electricity, but stored annihilation potential. You're not fueling a ship so much as building an economy around a stockpile. And you must ask what kind of civilization chooses to keep that much explosive energy in inventory, year after year. Storage is the next barrier, and it is where the word containment becomes literal. Antimatter cannot touch normal matter, which means it must be held in electromagnetic traps, as ions or neutral atoms in special configurations. Those traps require power, stability, and fault tolerance that must persist for years without interruption. The ship must treat containment like life support, because for antimatter the distinction disappears. A containment failure is not a leak, and it is not a slow seep you can patch. It is an explosion and a radiation event because annihilation happens at contact and it happens instantly. The engineering must assume that every component can fail, and then prevent any failure from becoming contact between antimatter and the walls. That means layers of isolation, fast shutdown logic, and the kind of conservative design that erases much of antimatter's theoretical elegance. Even if perfectly stored, annihilation products are difficult to use, and the difficulty is geometric. Proton, antiproton annihilation produces high-energy gamma rays and pions, and much of that energy is penetrating radiation. Penetrating radiation is hard to collimate into thrust, because it ignores mirrors and magnetic fields. You can try to absorb it and re-emit it, but absorption is heat, and heat is the problem you are trying to escape. If you try to turn annihilation into a rocket, you face a conversion problem that does not go away with enthusiasm. You must channel energy into directed momentum, not isotropic radiation, and that requires interaction. Otherwise you get heat and lethal flux, not efficient acceleration. The visuals become harsh, shielding blocks thick as walls, cooling loops glowing faintly, and the sense that the engine is a reactor you stand far away from. Shielding against annihilation radiation adds mass, and mass drives the energy bill back up, and the loop closes. The more energy dense your fuel, the more extreme your containment and shielding, and the less of the theoretical advantage remains. The spreadsheet perfection dissolves into engineering compromise. Antimatter does not remove constraints, it compresses them into smaller volumes with higher stakes. So antimatter becomes a statement about civilization, not just propulsion, because it demands a culture of precision and risk. A society that can safely produce, store, and launch antimatter at scale is a society with industrial capacity beyond anything we have built. It must also accept existential risk as routine and treat it like logistics. The question is not only can we do it, but who keeps it safe, and for how long? When internal fuel looks impossible, proposals move the fuel off the ship, and that shift changes the story. Beamed propulsion relocates the energy source to a distant transmitter, and the ship carries a sail or receiver. It rides a beam like a surfer rides a wave, except the wave is a focused power plant. The visuals pull back to a planetary scale. An array on a desert plateau or in orbit synchronized like a single instrument. This changes the rocket equation story, and it changes the silhouette of the craft. The vehicle can be extremely light, because it does not carry propellant for the main acceleration. It also changes the mission story, because the true engine is no longer the ship, it is the infrastructure behind it. The ship becomes a projectile with a delicate interface, and the beam becomes the thing that must not blink. Laser sails are the most discussed version, partly because lasers feel like the right tool for a futuristic age. A powerful laser array pushes on a reflective sail using photon momentum, and the physics is clean. The thrust is small per watt, but it can be sustained, and the sail can in principle reach high fractions of C. The image is striking, a thin, shimmering membrane kilometers wide catching a tight column of light that is invisible except where it scatters. Microwave sails trade shorter wavelengths for easier generation, and larger apertures, and that trade is practical rather than magical. They can push larger sails with less extreme optics and more forgiving surface tolerances. They still face the same fundamental issue, because beams spread with distance. The difference is not whether diffraction exists, but how brutally it punishes you for a given wavelength and transmitter size. Diffraction is the quiet enforcer here, and it is as unavoidable as gravity. Any finite aperture produces a beam with a minimum divergence set by wavelength over aperture size. Over interstellar distances, even tiny divergence becomes an enormous spot size, and the spot size is lost thrust. The visuals can be simple: a beam that begins as a needle and becomes inevitably a widening cone. To keep a beam tight over millions of kilometers, you need an aperture measured in kilometers and exquisite phase control. To keep it tight over astronomical units, you need apertures that become planetary engineering projects. The transmitter begins to look less like a telescope and more like a continent. And the control problem becomes a choreography of timing. Every element phase-locked, every drift corrected, every vibration damped. If the beam spreads, most energy misses the sail, and missed energy is not just waste. It is a hazard to anything in the beam path because it is still power traveling at light speed. It also represents a power plant firing into space with low coupling efficiency, and efficiency is destiny at these scales. A civilization can afford waste in small machines, but not in a system that runs like a star for years. Sail materials become another wall, because the sail is both engine interface and structural element. The sail must be extremely light, highly reflective, and able to survive intense flux without heating and tearing. It must also survive impacts and charging in space while remaining optically perfect. Even tiny wrinkles matter, because they change the beam's pressure distribution and can twist the sail into instability. A sail that absorbs even a small fraction of a multi-gigawatt beam becomes a radiator problem again, and the numbers escalate quickly. It heats, it re-radiates, and it can fail catastrophically when a small hotspot runs away. The sail is not just pushed by light, it is cooked by imperfection. In a close-up, the failure would begin as a barely visible discoloration, then a tear that races outward as tension redistributes. Pointing and tracking become mission-critical, and they push control systems into the realm of astronomical precision. The transmitter must keep the beam on a sail that's accelerating away with tiny angular tolerances. Over long distances, microradian errors become thousands of kilometers of miss, and the sail slips out of the spotlight. The ship's navigation becomes a dance between beam riding stability and the need to correct course without losing the push. Beam propulsion also complicates deceleration, which is the part that tends to vanish in optimistic sketches. You can accelerate outward with a home-based beam, but braking at the destination requires another beam, a reflection scheme, or a magnetic sail that pushes against the interstellar medium. Each option adds infrastructure, or adds time, and time is exposure. The story of arrival becomes as hard as the story of departure, because speed is only useful if you can shed it. So the beamed sail concept trades onboard fuel for external commitment, and that commitment must persist across years. It asks for a transmitter array, power generation, and control systems that operate reliably for long durations. It asks for an energy budget comparable to national grids, focused into a narrow cone. The ship may be small, but the civilization behind it must be vast, and willing to keep paying long after the launch celebration ends. This is not automatically impossible, and it is not a violation of physics. It is a different kind of impossibility, one made of economics, governance, and patience. It demands a stable, wealthy civilization that can build megastructures and keep them aligned across political eras. The question becomes sociological as much as technical. What institutions last long enough to keep a beam on target? At this point, the narrative attracts reactionless drives because they promise to erase the accounting. They promise thrust without propellant, without beams, and without exchanging momentum with anything external. They promise motion as a free lunch, and free lunches are always popular. The visuals here are always the same: a small device on a bench, a claim of anomalous thrust, and the hope that the universe has a loophole. A cosmologist's lens makes the problem plain, and it does not require cynicism. Momentum conservation is tied to the symmetry of space, and energy conservation is tied to the symmetry of time. These are not optional rules that can be engineered around. They are the structure of the laws themselves. When you test them, they hold across particle physics, chemistry, and the trajectories of planets. If a device produces net thrust in a closed system, it implies momentum appears from nowhere, which is already a crisis. If it also produces useful work, it implies energy appears from nowhere, and that is a deeper crisis. Such devices collide with Noether's theorem and with every tested domain of physics. The burden of proof is not high because scientists are pessimists, but because the claim is that the foundation is wrong. Claims of reactionless propulsion often hide an external interaction, and the hiding can be subtle. They push against electromagnetic fields, against expelled photons, or against the environment in ways that are not properly accounted. When you close the system boundaries correctly, the thrust vanishes or the cost reappears. The mystery dissolves into bookkeeping, and the universe's ledger balances again. Photon rockets are the honest extreme case because photons do carry momentum, and they do count as reaction mass. They are reaction mass that you must manufacture as pure energy, and that is expensive. The thrust per watt is fixed by C, which means enormous power for modest acceleration. A photon drive is simple in principle, yet merciless in scale, because the speed of light is both your tool and your limitation. That power again becomes heat somewhere, because real systems are not perfect and because optics are not lossless. Even if you could generate pure photon thrust, your power plant and mirrors would dissipate losses. The waste heat wall returns because it always returns, and it does not bargain. Every % of inefficiency becomes a thermal load that must be carried, spread, and radiated. The waste heat wall is the chapter's central reveal, and it is easy to underestimate because it is quiet. In vacuum, heat does not convect away, and it does not conduct into the void. It leaves as infrared photons, and the rate is limited by temperature and area. The ship's survival depends on a slow, steady glow, like an ember that cannot be allowed to flare. A high-power interstellar engine is therefore also a luminous object, whether it wants to be or not. It must glow to survive, because glowing is how it cools, and cooling is how it stays intact. If it tries not to glow, it overheats, and overheating is failure. The visuals become stark, a dark ship with broad, faintly red panels, shining in infrared even when the engines are silent. This creates a design paradox that shows up in every serious study. To go fast, you need high power, and high power demands large radiators. Large radiators increase mass and vulnerability, and they also increase the ship's interaction cross-section with dust and gas. The ship becomes a compromise between the desire to be small and the need to be thermally large. Even if your propulsion is beamed and your ship is light, onboard systems still generate heat, and that heat must leave. Guidance, communication, computation, and life support reject waste heat, and they do it continuously. A crude craft cannot be a perfect thermodynamic machine, because life is not reversible. The mundane becomes mission critical: fans, pumps, heat exchangers, and the quiet reliability of valves that must never seize. If your engine is fusion, neutron heating and inefficiencies dump power into the structure, and the structure must survive it. If your engine is antimatter, gamma rays and secondary particles deposit energy in shielding, and shielding must radiate it. If your engine is electric, power electronics and motors still dissipate heat, and the radiators still grow. The details change, but the outcome does not. Entropy must be exported, and space offers only photons as the exit. So the ship becomes a thermal management problem disguised as a propulsion problem, and the disguise is thin. The radiator area becomes a hard constraint on sustained acceleration, because it caps continuous power. It is not a matter of better insulation, because insulation traps heat and makes the crisis faster. The ship cannot hoard heat for long, because heat is not a resource here, it is a threat. This is where conservation laws act as the quiet enforcer, and they enforce more than momentum. You must exchange momentum with propellant, photons, or an external beam, and you must also dispose of entropy as waste heat. Every real process increases it, and the universe insists you pay that bill in photons. The laws are not dramatic, yet they are absolute, and they shape every plausible starship into something wide, bright, and careful. Engineering can approach limits, and it can do astonishing things with magnets and materials. It cannot repeal those limits, because they are not engineering choices. You can build better coils, better radiators, and better control systems, but you cannot build a ship that accelerates hard while producing no waste heat and requiring no momentum exchange. The dream does not fail because we lack imagination, but because the universe is consistent. The tension now shifts from speed to survivability, and the visuals change with it. A ship powerful enough for interstellar delta V is also a machine that must handle extreme radiation, extreme heat flux, and extreme reliability demands. The mission becomes a test of long-duration industrial control, performed far from any repair dock. Every subsystem must be both efficient and forgiving, because the ship cannot afford brittle perfection. So the fuel that does not exist is not only a substance, and it is not only a missing reaction. It is a missing combination of properties: energy-dense, safe, storable, throttleable, and compatible with manageable waste heat and manageable shielding. Every candidate fails a different way, and each failure is physical. The failures are not negotiable, because they are anchored in cross-sections, material strengths, and thermodynamic limits. Chemical fuel fails by low energy density, and the rocket equation punishes it with exponential mass. Fission fails by mass, shielding, and heat rejection, even when the reactor itself is reliable. Fusion fails by ignition, confinement, and neutron damage, even when the equations look generous. Antimatter fails by production, storage, and radiation handling, even when the energy density is perfect. Beamed propulsion avoids onboard fuel, but it demands a civilization-scale transmitter and precision over astronomical distances. Reactionless drives avoid the rocket equation only by colliding with conservation laws, and conservation laws do not blink. The universe keeps its books, and it keeps them in ink that does not fade. And if the accounting feels harsh, it is because reality is the ultimate auditor. From here, we stop treating energy as a number on a chart and start treating it as a physical substance. It has mass, it has heat, it has radiation, and it has consequences that fill the ship's design. The more energy you concentrate, the more violently the ship must manage it. The question becomes less, how fast, and more, how long can the machine endure its own power? The chapter ends by tightening the trap because every solution opens a new constraint. Suppose you somehow pay the energy bill and build the radiators, and suppose your materials survive the radiation. Suppose you solve the fuel problem with infrastructure, or with physics we have not yet mastered. You still must cross the space between stars, and you must do it while carrying a machine that cannot ever truly relax, because relaxation is how failures begin. And the space between stars is not empty. At high speed, it becomes a particle beam aimed at your hull, and the next barrier is not cost. It is lethality. The interstellar medium, thin as it is, becomes dense in your frame, and each atom arrives with the violence of a bullet. So we turn the page from engines to environment, and the mood darkens. The void is about to stop behaving like a vacuum and start behaving like a weapon, and the ship will have to endure every kilometre of it. Chapter 3 ended with a warning that the void is not empty. Chapter 4 makes that warning physical, because speed turns thin space into a weapon. On screen, the camera drifts through blackness that looks clean and silent. Then the image fills with faint haze. The haze is not artistic license. It is the interstellar medium, the material between stars that refuses to vanish. The shot lingers as if the lens is learning to see what humans usually ignore. Tiny motes of light, barely there, slide across frame like dust in a sunbeam, except the sunbeam is a light year wide. Between the stars is the interstellar medium, a mixture of gas, dust, fields, and radiation. It is sparse by Earth standards, yet it fills every light year you must cross, and it never gives you a true vacuum. In many regions near the Sun, the gas density is roughly 1 atom per cubic centimetre. That number sounds like nothing, yet it is a number you multiply by distance. An interstellar distance is the longest lever in nature. A cubic centimetre is the size of a sugar cube's corner, and 1 atom inside it feels like absence. But stretch that cube into a tunnel that runs for trillions of kilometres, and the arithmetic stops feeling abstract. Some clouds are denser, some cavities are thinner, and none are truly zero. Astronomers map these regions with absorption lines and radio emission, watching how starlight is subtly bitten away by intervening atoms. Those absorption lines are fingerprints, thin dark notches where specific atoms steal specific colours. Hydrogen marks one set of lines, sodium another, and molecules add their own patterns, letting us infer what we cannot photograph directly. Radio telescopes add a second sense, listening for the 21-centimetre whisper of neutral hydrogen. That signal comes from a quantum flip in the hydrogen atom, and it lets astronomers sketch vast structures that optical light barely hints at. Most of that gas is hydrogen, with helium and trace heavier atoms mixed in. The chemistry is simple, but the consequences at high speed are not, because even simple atoms can become radiation sources when they strike fast. Hydrogen in the interstellar medium is not always the same physical state. Some is neutral atomic hydrogen, some is ionized plasma, and some is locked into cold molecular clouds where hydrogen pairs into H2. Each phase has its own temperature scale, from tens of Kelvin in cold clouds to millions of Kelvin in hot, rarefied bubbles. The same element can behave like a frigid fog, a warm breeze, or a thin, electrically active soup. Those phases matter because they set temperature, pressure, and how strongly the gas couples to magnetic fields. They also matter because they change what your ship meets first: neutral atoms that slip through fields, or charged particles that spiral along them. Neutral atoms can pass through a magnetic shield as if it is not there, which is the uncomfortable point. Charged particles, by contrast, feel the Lorentz force and curve, and that difference shapes every defensive idea. Dust is rarer than gas, yet it carries most of the danger for fast travel. Dust grains are solid mass, and solid mass does not negotiate on impact, especially when the closing speed is a fraction of light. If the gas is a thin mist, dust is gravel hidden in the mist. You do not need much gravel to change a journey, because a single strike can concentrate the entire risk into one instant. Interstellar dust spans a distribution of sizes from nanometer smoke to micron grains. The smallest grains behave almost like large molecules, while the micron grains behave like tiny rocks with sharp edges and stubborn inertia. Astronomers infer those sizes from how dust reddens starlight, scattering blue wavelengths more strongly than red. The sky between stars is not just darker, it is tinted, and that tint is a measurement of grain physics. Larger grains are much rarer, yet a single one can dominate the risk. The distribution is steep, so big grains are scarce. But probability is not comfort when one event can end a mission. This is the logic of extreme travel, where averages are less important than tails. The mission does not fail because of typical dust, it fails because of the one grain that was never supposed to be there. Dust is not uniform in composition, and that adds uncertainty to every calculation. Many grains are silicates, some are carbon-rich, and some carry icy mantles in colder regions, which changes density and how they fragment. In colder zones, those icy mantles can trap simple molecules like water, carbon monoxide, and ammonia. Heat them, shock them, or irradiate them, and they release gases and radicals that change the local chemistry in a flash. Even the shape of a grain matters at high speed, because a porous aggregate shatters differently than a compact sphere. In the lab, hypervelocity impacts show that fragmentation physics can flip with small changes in structure. A fluffy grain can behave like a brittle snowball, spreading its energy quickly into a wide spray. A compact grain can behave like a bullet, delivering a deeper, narrower shock before it vaporizes into plasma. Magnetic fields thread the medium at microgauss levels, shaping plasma and guiding charged particles. They do not remove matter, and they do not stop neutrals, so they become a partial filter rather than a wall. On a visualization, field lines arc like faint threads across a star map, bending around clouds and cavities. Those threads are real, inferred through polarized starlight and Faraday rotation, and they give the medium a hidden geometry. Faraday rotation is a subtle twist in the polarization of radio waves as they cross magnetized plasma. It is one of the ways we turn invisible structure into a map, and it reminds us that space has texture. Cosmic rays also fill interstellar space, mostly protons and heavier nuclei moving near light speed. They arrive from supernova remnants, jets, and the broader galaxy, carrying energies that dwarf what human accelerators routinely achieve. Some cosmic rays are so energetic that a single nucleus carries the kinetic energy of a thrown baseball, compressed into a particle smaller than an atom. That comparison is real, and it is part of why shielding is never a simple box. Cosmic rays are not just a background hiss of particles, they are a radiation climate, shaped by the solar wind near the Sun, and by the galaxy's magnetic turbulence farther out, and their intensity varies with location and time. Near Earth, the heliosphere acts like a breathing shield, modulating cosmic rays with the solar cycle. Farther out, that protection fades, and the ship enters a more exposed regime where the galaxy sets the rules. At ordinary spacecraft speeds, these ingredients are background noise. At 0.1 C, the same ingredients become a continuous stream of high-energy collisions, and the ship becomes an experiment in impact physics. The scaling is simple enough to say out loud, and brutal enough to matter. Kinetic energy is about 1/2 mv squared in the Newtonian limit, which is accurate enough at 0.1 C to make the point sting. Relativity is present even here, but it is not yet the main actor. The main actor is still velocity, because the square in that equation punishes ambition with mathematical indifference. That equation hides the real lesson, because v is the lever that dominates. Multiply v by 10 and energy rises by a factor of 100. So speed is not a gentle upgrade, it is a quadratic escalation. It also changes momentum, which matters for how deep damage propagates into structures. Even if energy can be absorbed as heat, momentum must still be redirected, and redirection is what creates shock and fracture. At 0.1 C, v is about 30,000 kilometers per second. Even a speck of mass carries energy that resembles an explosive, because motion is stored energy that must go somewhere when it stops. A useful mental image is to imagine a rainstorm, then imagine the raindrops replaced by bullets. The density is low, but the relative speed turns each encounter into a violent conversion of motion into heat and shock. The film could cut to slow-motion impacts in a lab chamber, where a tiny pellet hits a target and blossoms into a bright flash. The flash is not fire in air, it is matter turning into plasma under sudden compression. Start with a hydrogen atom because it sounds harmless. In the ship's frame at 0.1 C, that atom hits like a particle accelerator projectile, and it arrives with enough energy to ionize and excite whatever it touches. Ionization means electrons are stripped away, and stripped electrons do not stay quiet. They recombine, they emit photons, and they create a local radiation field right where the ship is already stressed. One atom is not the problem, because one atom deposits a tiny amount of energy. The problem is flux, because you meet an ocean of atoms over light years, and the ship's nose continuously sweeps them up. In the ship's frame, incoming gas is not a gentle breeze. It is a beam compressed into the forward direction by aberration, and each atom becomes a microscopic hammer that never stops swinging. Aberration is the same effect that makes rain seem to come from straight ahead when you run. At high speed, the sky itself tilts forward. Particles and photons crowd into a narrowing cone. Each impact can knock atoms out of your hull, sputter surfaces, and generate secondary particles. Over time, the hull erodes like stone under sand, except the sand is atomic and the wind is relativistic. Sputtering is a deceptively simple process with a cruel outcome. An incoming particle transfers momentum to lattice atoms, and if enough energy reaches the surface, atoms are ejected into space one by one. Those ejected atoms do not simply vanish either. Some become a thin cloud around the ship, and that cloud can interact with fields, charge states, and sensors, an engineered object dragging its own environment along. That slow loss changes surface chemistry and optical properties, which matters for thermal control coatings and sensor windows. A surface that starts smooth and reflective can become rough, dark, and thermally unpredictable. Now scale up to dust, because dust is where the story turns dark. A micron-sized grain has billions of atoms, and it arrives with the same velocity, so the energy scales with mass while the speed stays fixed. At 0.1 C, a grain's kinetic energy can be comparable to a grenade or worse, depending on mass. The exact number varies, yet the trend is fixed, and the trend is what design must respect. To the camera, a grain is invisible, but the impact is not. A brief white flare blooms on the shield's face, then a spreading bruise of molten material cools into a crater rimmed with glassy residue. The ship does not need to hit an asteroid to be destroyed. It only needs one unlucky encounter with a grain large enough to overwhelm local shielding, because the interaction is closer to detonation than to collision. In hypervelocity impact experiments, a fast projectile does not remain a projectile for long. It vaporizes, the target vaporizes, and the contact region becomes a plasma that expands violently into surrounding material. At these speeds, the concept of hardness changes, because everything behaves like fluid under shock. The strength of the material matters less than how it manages energy, phase change, and fracture under extreme strain rates. That expanding plasma is not a clean hole punch. It is a spray of energized fragments, shock fronts, and electromagnetic noise, and it can couple into nearby structures in ways that are hard to predict. This is why dust becomes the primary hazard in most serious interstellar studies. Gas causes steady radiation and gradual damage, while dust can end the mission instantly, and mission planners fear the single-point failure. The danger comes in two forms that stack rather than replace each other. There is cumulative erosion from countless small impacts, and there is catastrophic failure from a rare large one, and both must be engineered against. Cumulative erosion is slow, yet it is relentless at high speed. Every impact excavates a tiny crater, ejects material, and roughens the surface, leaving a scar map that grows with every kilometre. If the visuals linger on the ship's nose, the metal does not stay pristine. It becomes frosted with pits, then crazed with microcracks, then layered with repairs that look like geological strata. The ship begins to resemble a meteorite, its leading face darkened and textured by countless tiny wounds. The irony is sharp. The craft becomes a piece of space weathered by the very space it crosses. Roughness matters because it changes thermal behaviour and increases sputtering yields. It also creates weak points where later impacts can spool larger flakes, which accelerates damage in a feedback loop. Spallation is the violent cousin of erosion, where shock waves fracture material and eject chunks. At 0.1 C, even small projectiles can drive extreme shock pressures, pushing materials beyond their elastic limits in an instant. Shock physics has its own vocabulary, because ordinary intuition fails. A shock wave compresses material faster than it can respond, raising temperature and pressure so quickly that solids behave like fluids for microseconds. In that microsecond, crystal lattices collapse, voids nucleate, and cracks race faster than the eye can follow. When the pressure releases, the material does not return to its old shape. It remembers the violence as damage. Those shocks can propagate into structural layers, damage tanks, and compromise pressure vessels. A shield that survives one hit may be weakened for the next, because internal delamination can hide behind an intact surface. Layered composites can help, yet they also introduce interfaces where cracks can run. Metals can deform plastically, ceramics can shatter, and each material trades one failure mode for another. There is no perfect wall. Engineers learned these lessons in Earth orbit, where millimetre debris can puncture satellites at mere kilometres per second. The interstellar case is the same story, told with a harsher scale and fewer rescue options. Electronics are also vulnerable, because impact plasmas create electromagnetic pulses and particle showers. A single event upset becomes a cascade if redundancy is thin, and the ship's brain can be rattled by its own collisions. A particle shower can mimic a storm of cosmic rays, flipping memory bits and triggering latch-ups. Designers can harden circuits and add error correction, yet the environment at the nose is an adversary that keeps changing. So the ship's front becomes a sacrificial zone designed to be damaged on purpose. Interstellar travel begins to resemble armour design more than aircraft design, and the language shifts from aerodynamics to survivability. The simplest shielding idea is thickness, because more material absorbs more damage. Thickness also means mass, and mass is the bill. Chapter 2 already posted, waiting with compound interest. A thick monolithic shield can stop small particles by spreading their energy into heat and deformation. It can also transmit shock, and it can crack under repeated loading, especially when thermal gradients and impacts combine. Thermal gradients matter because the nose is heated by continuous bombardment. Even if each impact is tiny, the integrated power can warm the forward face, and hot materials can weaken or creep over time. Creep is slow deformation under stress, and it becomes relevant when a structure stays warm for years. The ship is not just surviving impacts, it is surviving a long, subtle bake under constant microscopic assault. Whipple shielding offers a different strategy, using a thin bumper spaced ahead of a main wall. The bumper breaks a projectile into plasma, and the cloud spreads before the rear wall, reducing peak pressure on the structure behind it. This works well for orbital debris at kilometers per second, and it can help at higher speeds. Yet at 0.1c, the energy density is so high that spacing and materials become extreme, and the design margins shrink. At very high speeds, the bumper can become a plasma generator that sprays the rear wall with energized debris. The shield still helps, but it must be tuned so the cure does not become a second wound. A Whipple shield must be large, layered, and carefully engineered to avoid turning into its own shrapnel. Each layer adds mass, and each kilogram multiplies propulsion demands, so protection and propulsion become a coupled problem. Some proposals add sacrificial ice or foam blocks at the nose, replenished or thick enough to last the crossing. The idea is simple, because ablation is predictable, and predictable loss is easier than unpredictable fracture. Ablation is also expensive, because you must carry the sacrificial mass from the start. You accelerate it, protect it, and then throw it away as damage, which is a painful trade when energy is already scarce. Ice has attractive properties in theory, because it is hydrogen-rich and can slow incoming particles efficiently. Yet ice also sublimates, cracks, and changes shape, so the engineering becomes a battle against thermal management and structural stability. A camera might show the ice nose glowing faintly, venting wisps of vapor into vacuum as it warms. The vapor freezes into glittering crystals that trail behind, a beautiful plume that is also lost mass. More ambitious concepts use a forward dust cloud, released ahead of the ship to pre-impact incoming grains. The ship rides behind its own artificial debris field, hoping to break threats before they reach the hull. That strategy creates a controlled collision zone, yet it demands constant replenishment and careful shaping. It also risks increasing your own local hazard if control fails, because a protective cloud can become a minefield. The cloud must be dense enough to matter, but not so dense that it becomes the primary source of impacts. That balance is delicate, and it shifts as the ship accelerates, decelerates, and passes through regions of different ambient density. Magnetic shielding is often suggested because fields can deflect charged particles. It can reduce some cosmic ray exposure, and it can shape plasma around the hull, potentially steering ionized gas away from sensitive surfaces. Magnetic shielding has a hard limit that cannot be wished away. Neutral dust grains and neutral atoms do not respond strongly to magnetic fields, so a magnetic bubble is not a universal umbrella. Even charged dust can become neutralized by electron capture and impact processes. The medium is not a clean beam of ions, and the ship cannot assume charge, especially when collisions constantly exchange electrons. Electrostatic deflection faces similar limits because it requires high voltages and large field regions. It can also attract charged particles and increase local heating, turning a defensive field into a collector of trouble. So shielding becomes a layered compromise, mixing mass, spacing, and fields. Every layer reduces one risk while increasing another, usually in mass and complexity is its own failure mode. That mass penalty feeds back into the energy penalty from earlier chapters. More shielding means more mass to accelerate and more energy to reject as waste heat, and waste heat must be radiated into space. The loop tightens again, because the environment forces you to carry armor. The armor forces you to carry energy, and the energy forces you to carry radiators, which are fragile surfaces that want to be wide and thin. Radiators are particularly awkward in a shooting gallery. They must expose area to space to shed heat. Yet exposed area is exactly what impacts punish, so the ship must hide its heat rejection behind geometry and redundancy. The visuals can emphasize this contradiction, with slow pans along folded radiator panels, tucked like wings behind the main shield. They look delicate, almost biological, as if the ship is protecting its own skin. At 0.1c, the ship is also a radiation problem even before considering dust. The interstellar medium becomes a forward-facing radiation source in the ship's frame, because collisions and relative motion reshape the spectrum of what arrives. Relativistic effects begin modestly at 0.1c, yet they point toward a worse regime. Aberration concentrates incoming particles and photons into the forward hemisphere, narrowing the sky into a bright, dangerous cone. The forward sky brightens, not because space changes, but because your motion changes what you intercept. The ship's nose becomes the place where the universe arrives, and the rest of the sky becomes comparatively quiet. Consider the cosmic microwave background, the faint 2.7 Kelvin glow filling all space. In your frame, the forward part is blue shifted to higher frequency, as if the universe's oldest light is compressed into a tighter colour. At 0.1c the shift is small, yet it is a preview of what happens at higher gamma. Push towards 0.5c and 0.9c and the forward background hardens, sliding from microwaves toward infrared and beyond. That is not just a change in colour for a camera sensor. Higher frequency photons carry more energy per photon, and a field that was once harmless can become a heating and radiation load. Starlight also shifts, and the forward direction becomes more energetic. Photons that were infrared can move toward visible and ultraviolet in the ship's frame, changing how coatings age and how materials charge. Materials that are stable in one spectrum can degrade in another, because ultraviolet can break chemical bonds and create surface charging. The ship's skin becomes a laboratory for photochemistry, driven by motion rather than by a nearby star. At high enough speed, the forward photon field becomes a radiation headwind. Shielding then must handle not only impacts, but also sustained high-energy photon flux, which can penetrate and generate secondary electrons. Cosmic rays add another layer, because they are already relativistic in the galaxy frame. Your motion changes their spectrum and angular distribution, increasing forward exposure, and the ship's shielding must cope with particles that ignore simple barriers. High-energy nuclei can punch deep into matter, fragmenting atoms and producing cascades of secondary radiation. A thick shield can reduce dose, yet it can also create more secondaries, so the best protection is not always the most mass. This is one of the counterintuitive lessons of radiation physics. More material can mean more interactions. The goal becomes moderation and geometry, not brute force, and that goal is hard when mass is precious. Radiation is not only a dose problem for biology, it is a materials problem for everything. It embrittles polymers, degrades solar cells, and flips bits in memory, slowly turning precision systems into unreliable ones. A crewed ship must therefore treat radiation as a life support parameter. The habitat must be buried behind mass, and mass again becomes the recurring cost, as unavoidable as the distance itself. Even if the crew is protected, the ship's forward systems still take the hits. Sensors, antennas, and radiators cannot all hide behind meters of shielding, so designers must decide what can be sacrificed and what must endure. This forces design choices that feel alien compared to near-Earth spacecraft. You either accept a short mission with high risk, or you build a slow fortress, and either way the medium dictates your posture. Now the navigation problem arrives, and it is not solved by better maps. At relativistic closing speeds, detection range must be enormous to allow reaction time, and enormous is a hard requirement to satisfy. If you are moving at Pointe-Yosti, you cross 30,000 kilometers every second. A 1-second delay is a continent of travel, and a minute is a planetary scale, so hesitation becomes impact. Sensors also face physics limits because small objects are dim and hard to detect. A micron grain does not reflect much light, and it does not announce itself, so your instruments must search for almost nothing against almost everything. Even if a grain scatters a few photons, those photons must reach your detector, be distinguished from noise and be processed in time. That chain has latency, and latency is the enemy when closing speed is relentless. The forward view is also contaminated by your own motion, because any dust you strike can create a glowing wake of plasma and fragments. The ship may be flying through a self-made fog of consequences, and sensors must see through it. Radar and LiDAR can probe ahead, yet their signals travel at sea. At 0.1c, the time between detection and impact can be too short for evasive maneuvers, and the power requirements for long-range detection can be severe. Even a perfect detection does not guarantee a dodge, because acceleration capability is limited by propulsion and by structural loads. The ship is not a fighter jet, and at interstellar scales it may be committed to its path. The ship cannot dodge what it cannot see, and it often cannot see what can kill it. Navigation becomes probabilistic, closer to risk management than steering, and mission planners think in distributions rather than guarantees. This is not a new anxiety in spaceflight, only a magnified one. Early spacecraft worried about micrometeoroids, and engineers built Whipple shields for Earth orbit, but interstellar speed turns a manageable hazard into a defining constraint. The first interplanetary probes carried micrometeoroid detectors, counting tiny impacts like raindrops on a roof. Those early counts helped calibrate fear with data, yet they also showed how much of space is still unknown at small scales. You can attempt to choose routes through lower density regions, avoiding known clouds and filaments. Yet the interstellar medium is structured on many scales, and maps are incomplete, especially for small-scale dust clumps. Local density can vary, and dust can be clumpy. A safe corridor in a model can still contain a rare grain, because statistics do not guarantee mercy, and the universe does not sign contracts. This is the shooting gallery aspect, and it deepens the mood of the film. Space is not an empty hallway. It is a thin storm you must cross at bullet speed, and the storm is invisible until it strikes. The ship's front must be treated like a continuously failing surface, monitored and rebuilt in flight. That implies repair capability, spare material and autonomous maintenance, because you cannot pause in interstellar space to visit a dry dock. A camera could linger on robotic arms crawling over the nose, laying down fresh layers like a 3D printer in vacuum. The repairs would look calm, yet every patch would be an admission that damages the normal state. Those robots would need their own sensors, their own redundancy, and their own tolerance for radiation upsets. Maintenance becomes a subsystem as critical as propulsion, because survival is a continuous process rather than a one-time design choice. Autonomy matters because communication cannot rescue you in time. Even at a few light years, messages take years, and emergencies unfold in seconds, so the ship must be its own first responder. A mission to Alpha Centauri has a minimum one-way delay of 4.37 years. Mission control becomes a historian, not a partner, and the crew becomes its own government, writing policy in real time under pressure. That isolation changes decision-making, accountability, and psychology. The ship must carry not only tools and parts, but also authority and the burden of irreversible choices, because there is no quick appeal to Earth. It also changes engineering philosophy, because remote troubleshooting is mostly impossible. Systems must be self-diagnosing, self-repairing, and tolerant of unknown failure modes, since the medium will invent failures you did not rehearse. The interstellar medium therefore attacks the mission on multiple fronts at once. It erodes the hull, irradiates the ship, complicates navigation, and forces autonomy, and each front amplifies the others. At 021C, these hazards are severe but not yet maximal. The chapter's deeper point is that every push toward higher speed makes the medium more violent, and the violence rises faster than the intuition expects. The same velocity that shortens travel time increases impact energy, increases forward radiation, and reduces reaction time. Speed is still a cascading liability, now expressed as lethality, and the ship must pay for every gained month. So the barrier is not only the energy to go fast and not only the fuel to sustain it. The barrier is that the space between stars is an active environment at relativistic speed, and it behaves like an obstacle course made of near nothing. A viewer might still ask for a clever shield, a smarter sensor, a better material. The story does not deny progress, yet it insists on the compounding structure, where each solution drags a new requirement behind it. To reduce risk, you add shielding and redundancy, and that adds mass. To move mass quickly, you add energy and power, and that adds heat and radiators, which must survive the same environment. To protect radiators and sensors, you add more structure, and structure adds mass again. The interstellar medium turns every design choice into a feedback loop, and the loop tightens as speed rises. Suppose, for a moment, that we solve propulsion and shielding anyway. Suppose our ship can endure the thin storm without being sandblasted into failure, and suppose the forward cone of radiation is tamed to survivable levels. The next question is quieter and more final. Can humans survive the time it takes, even if the metal survives, and even if the ship's systems remain obedient? Because the next barrier is not a dust grain or a gamma ray. It is flesh, aging, and the social fragility of long voyages, stretched across years that cannot be skipped. We leave the shooting gallery and turn inward, toward biology and time. The universe does not only test our engineering, it tests what a human life can contain, and whether endurance is a technology we truly possess. Suppose for a moment that propulsion works and shielding mostly holds. Suppose the hull stays tight, the heat radiators glow steadily, and the navigation solution remains clean. The next barrier is not metal fatigue or dust impacts. The next barrier is the living system that must endure the crossing. Human biology is tuned to one gravity, one radiation climate, and one social scale. It evolved under a 1G constant that never turns off, under a magnetic field that blunts the worst of space, and inside communities that can disperse when tensions rise. Interstellar travel breaks all three at once, then asks stability for decades. That is the core tension, an environment that never relaxes, paired with bodies that expect relief. Even our circadian rhythms assume a planet that turns because light and darkness are built into our chemistry. It is not one unsolved problem. It is thousands of interacting problems that must all be solved together. A small change in sleep alters hormones, hormones alter bone turnover, bone loss changes, exercise needs, and exercise changes heat loads and water demand. The ship becomes a coupled system where biology pushes engineering, and engineering pushes biology back. The question is not whether humans can survive space. The question is whether a closed world can keep humans healthy while time keeps moving. Start with microgravity, because it attacks the body even in low Earth orbit. The visuals are deceptively gentle, astronauts floating like divers, hair drifting, tools hanging in midair. Yet inside the skeleton, the quiet machinery of remodeling begins to shift, and it shifts with biochemical certainty. Bone is not a static scaffold. It is living tissue that constantly renews itself, dissolving and rebuilding in response to stress. On Earth, every step sends microstrains through the femur, the pelvis, the spine. Cells called osteocytes sense that strain, then signal osteoblasts to build and osteoclasts to resorb. Remove load, and the balance shifts toward loss, because the body treats unused structure as excess mass. Calcium and phosphate drift out of the lattice, and the kidney must handle that extra mineral traffic. The result is not dramatic in a day, but it is relentless in a month. Astronauts lose bone mineral density and weight-bearing regions despite careful monitoring. The hip, the lumbar spine, the neck of the femur, these are the places that pay first. Imaging like DEXA scans and quantitative CT can track the thinning, and biochemical markers in blood and urine reveal accelerated turnover. The loss resembles accelerated osteoporosis, but it is not identical. It is a new physiological regime driven by unloading, altered fluid distribution, and changed signaling pathways. Microgravity also changes the architecture of bone, not just its density. Trabecular bone, the spongy lattice inside vertebrae and joints, can lose connectivity. Cortical bone, the dense outer shell, can thin in patterns that alter strength more than the numbers suggest. A small percentage loss in mineral is not a small percentage loss in fracture resistance. Strength depends on geometry, and geometry is what remodeling quietly edits. In visuals, the bone becomes a bridge whose beams are still present, yet subtly respaced and weakened. Muscle follows the same rule, and it does so with brutal clarity. Without constant resistance, muscle fibers shrink and weaken, and the nervous system stops recruiting them with the same precision. Postural muscles degrade fastest, because they evolved for continuous work against gravity. The calves, the quadriceps, the muscles that stabilize the spine, these are built for endurance, not idleness. At the cellular level, protein synthesis slows, breakdown pathways rise, and mitochondria adapt to a different demand. Strength loss is not cosmetic. It changes injury risk and basic mobility, and it changes the margin for error during emergencies. In a habitat, a fall is not a broken wrist and a trip to the hospital. It is a fracture in a place where surgery is hard, rehabilitation is limited, and the patient is needed for mission labour. Even the act of hauling a stuck valve or moving a water tank becomes a physiological challenge. When the ship is your only workplace, disability is not personal, it is systemic. The cardiovascular system also deconditions, and it does so in a way that looks like an invisible replumbing. In microgravity, fluids shift toward the head and chest, swelling faces and changing pressure in the eyes. The body interprets this as excess volume and reduces plasma, because it thinks it is overloaded. The heart does less work, then becomes less capable, as muscle mass and reflex control adapt to the new baseline. Over time, even red blood cell mass can change, altering oxygen delivery in subtle ways. Baroreceptors that normally regulate blood pressure learn the wrong lesson. Blood vessels lose some tone, and the autonomic system recalibrates around a world where blood does not pool in the legs. When astronauts return to gravity, orthostatic intolerance appears. Standing up can cause dizziness or fainting, and the simple act of walking becomes a negotiation with physiology. The visual contrast is stark. Floating grace in orbit, then trembling legs under Earth's pull. that is after months, not decades. It is a warning about what long missions would demand because time multiplies small deficits. A multi-decade voyage is not a longer version of a 6-month mission. It is a different category of risk, where chronic conditions emerge and then become the normal state. In that regime, you do not recover between exposures. You live inside exposure, and the baseline slowly shifts beneath you. Months matter because biology adapts quickly, and not always in helpful directions. The immune system shifts, the endocrine system shifts, and even the eyes can change, with spaceflight-associated neuro-ocular effects linked to fluid dynamics. Researchers track optic disc edema, globe flattening, and subtle vision changes that hint at pressure gradients in a headward-shifted body. The body is plastic, and plasticity is not automatically beneficial. It is simply responsiveness, and the environment of a starship is a persuasive teacher. Exercise is the main countermeasure we have, and it is already expensive. On the International Space Station, exercise is not a hobby. It is scheduled like maintenance, because it is maintenance, and it consumes crew time that could be used for repairs, science, or rest. It requires machines, maintenance, and spare parts, and it creates vibration that the station must absorb. The cost is not only mass and power, it is attention, the most limited resource in a complex system. The hardware itself is a visual symbol of the problem. Astronauts strap themselves to a treadmill with bungee harnesses, pulling their bodies down against elastic resistance. They use cycle ergometers that must be anchored so the rider does not spin the station. They lift on resistive devices that simulate weight with pistons and vacuum cylinders. The soundscape is mechanical, fans, clanks, straps, breathing, because the body is being reminded of Earth by force. Sweat beads float away if they are not captured, and every droplet becomes a maintenance issue. It also requires compliance, which depends on psychology and schedule. Even with rigorous exercise, bone loss is not fully prevented, and the variability between individuals is striking. Genetics, prior fitness, nutrition, and hormonal state all modulate outcomes. A countermeasure that works for one crew member may only slow decline in another. That variability matters on a ship because planning assumes averages while emergencies punish outliers. Exercise has limits because it is a partial substitute for gravity, not a replacement. Loads are intermittent and targeted, and they often fail to reproduce the subtle, constant micro-adjustments of standing, walking, and shifting posture. Gravity is continuous and whole body. The body senses that difference at the cellular level because mechanotransduction depends on frequency, direction, and duration of strain. Even connective tissues, tendons, ligaments, cartilage, expect habitual loading patterns that are hard to mimic. Even if you could exercise for hours, you would still face the problem of the remaining 20 hours. Bones respond to habitual loading, not heroic bursts. Muscles maintain tone through constant low-level activation, not just maximal contractions. The cardiovascular system expects a daily rhythm of standing, sitting, and moving through a vertical world. A ship that removes verticality removes a fundamental pattern. The question becomes uncomfortable. Can you schedule a substitute for a planet? So the narrative turns toward artificial gravity, because it promises to restore the missing constant. Rotation habitats are the classic idea, and they appear in diagrams with elegant simplicity. Spinor structure and centripetal acceleration becomes a gravity analogue, pressing bodies against a floor. The concept is simple. The implementation is not, because the inner ear and the structure itself both have opinions. Even the air behaves differently, with subtle pressure gradients and circulation patterns that engineers must anticipate. In a rotating frame, the vestibular system encounters unfamiliar physics. Turn your head, and the Coriolis effect generates cross-coupled accelerations that feel like a twist inside the skull. A glass of water poured in a rotating room arcs strangely, and a tossed object curves as if guided by an unseen hand. For a new crew member, nausea and disorientation can become persistent, especially during early adaptation. The visuals can linger on a hand reaching for a rail that seems to slide sideways, betraying intuition. The problem is scale. Small rotating ships create strong Coriolis effects because the rotation rate must be high to generate 1G at a small radius. High RPM means the inner ear experiences rapid changes during ordinary motion, and ordinary motion becomes extraordinary. A crew that cannot function is a mission failure, no matter how perfect the engines are. There is also the gravity gradient. Feet may feel heavy while the head feels light, and that mismatch can affect comfort and circulation. To reduce Coriolis problems, you increase the radius and lower the rotation rate. That pushes designs toward large rings, long spokes, or tether systems that stretch two masses apart. A larger radius makes the gravity gradient smaller too, so feet and head experience more similar acceleration. Yet large structures bring structural stress, vibration modes, and bearing or joint complexity. In visuals, the ship stops looking like a capsule and starts looking like architecture. Curving trusses, tensioned cables, and rotating habitats that resemble slow mechanical planets. They also increase mass and surface area, which matter for shielding and thermal control. A ring needs stiffness to avoid wobble, and stiffness means material. A joint between a spinning habitat and a non-spinning hub needs bearings, seals, and redundancy, because failure is catastrophic. The ship becomes a machine with moving parts that must run for decades, which is the hardest reliability problem of all. The maintenance schedule becomes a kind of ritual, because neglect accumulates silently in rotating machinery. A rotating habitat must also survive impacts and radiation while maintaining balance. Any mass redistribution changes spin stability, and stability is not just comfort. It is structural safety, because an imbalanced ring can induce oscillations that fatigue joints and trusses. Repairs become dynamic, because you cannot casually weld on a spinning ring without consequences. Every patch is also a mass change, and every mass change is a control problem. Even moving cargo becomes a navigation event, because the ship's moment of inertia is part of its identity. Artificial gravity also does not automatically solve everything. Partial gravity may still produce unknown developmental effects, because biology may have thresholds and nonlinearities. The minimum effective gravity for bone maintenance is not fully known, and it may differ by age and sex. The interaction with exercise, nutrition, and genetics remains uncertain. A rotating habitat can give you a floor, but it cannot guarantee a normal human body. It offers a new environment, not a return to the old one. There is also the question of transitions. If the ship has both spinning and non-spinning sections, crews must move between them. Passing through a rotating interface can be disorienting, and repeated transitions may carry their own adaptation costs. Even the design of doors, corridors, and handholds becomes physiological architecture. The ship's layout becomes a medical decision. In visuals, a simple hatch becomes a boundary between two physics regimes. Radiation is the next biological wall, and it does not wait for old age. Outside Earth's magnetosphere, the background is not empty. It is a rain of particles, some moving near the speed of light, some carrying enough energy to punch through centimeters of metal. Galactic cosmic rays are high-energy nuclei, protons, helium, and heavier ions like iron, that penetrate deeply and ionize as they pass. Their energies are so high that shielding becomes less like a wall and more like a statistical filter. Solar particle events deliver sudden bursts of protons and heavy ions, often tied to flares and coronal mass ejections. In visuals, the sun looks calm, then erupts in ultraviolet and X-ray imagery like a tearing veil. The ship, far from Earth's protective field, must treat the sun as both a light source and a hazard. A storm shelter becomes as essential as a reactor shield. The crew's response becomes procedural, alarms, dosimeters, a practiced retreat into the safest volume. Both sources produce damage that accumulates. Ionizing radiation breaks DNA strands, creates base damage, and generates reactive oxygen species that stress cells. High-let particles, especially heavy ions, produce dense tracks of ionization that are harder for the body to repair. The result is not just a higher probability of mutation, it is a different quality of injury, distributed across tissues over time. Some cells survive with subtle errors, and those errors can echo later as disease. Radiation risk is not only cancer decades later, although cancer is the headline. It includes cataracts, cardiovascular disease, and neurodegeneration, because blood vessels and neural tissue are sensitive to chronic insult. It includes impaired wound healing and altered immune function, which matter immediately on a mission. It is a chronic stressor that changes the baseline of health, turning minor problems into major ones. In deep time, risk is not a spike. It is a background hum. The intuitive solution is to add shielding, and in a diagram it looks like an easy fix. The real outcome is a trade that collides with mass and secondary radiation. High-energy particles strike shielding and create showers of secondaries, neutrons, fragments, and gamma rays, that can spread dose through the interior. Some materials can make the interior dose worse in certain spectra, because they create more harmful byproducts than they stop. The ship becomes a laboratory in radiation transport, whether it wants to or not. Hydrogen-rich shielding can help by moderating particles, because hydrogen nuclei are similar in mass to protons and can slow them efficiently. Water, polyethylene, and even stored food can be arranged as protective mass, wrapping crew quarters like a living bunker. Yet every kilogram of shielding is a kilogram you must accelerate and decelerate. The energy bill returns through biology, because propulsion limits determine mission duration, and duration determines dose. The trade is circular. Mass buys safety, but mass also buys time, and time buys exposure. Shielding is also geometry. A uniform wall is idealized, but ships are full of gaps, corridors, tanks, and equipment bays. Dose becomes anisotropic, meaning direction matters, and crew behavior becomes part of radiation protection. Where you sleep, where you work, and where you shelter during a solar event all change cumulative exposure. The habitat becomes a map of invisible gradients. In visuals, particle tracks light up a cross-section, revealing bright streaks where protection is thin. Radiation also attacks the ship's microbiology and chemistry, which is easy to forget because it is not dramatic. It degrades polymers, embrittling plastics and weakening seals. It alters drugs, breaking active molecules into less effective or even harmful compounds. It flips bits in electronics, forcing error correction and redundancy, and it changes surfaces that microbes live on. Over years, those changes accumulate into a different habitat, one that slowly drifts away from its original specifications. Materials age, coatings chalk, and microcracks become niches where biofilms can anchor. The microbial ecology that keeps a closed habitat stable is not static. It is shaped by radiation, humidity, cleaning practices, and the constant shedding of human skin and breath. The ship is never sterile, and it cannot be because humans are not sterile. The question becomes management, not elimination. An ecological problem disguised as housekeeping. Long-duration medicine is therefore not a clinic problem. It is a systems problem, because the ship is the clinic, and the clinic is also the farm and the factory. Immune function shifts in spaceflight, with changes in inflammation and viral reactivation documented in astronauts. Latent viruses like herpes viruses can reappear under stress, which is a reminder that the body carries its own history. Even minor infections can become complicated when recovery time competes with mission labor. The microbiome drifts under altered diet, stress, and environment. In a closed habitat, diet may be more uniform, fiber sources may change, and fresh foods may be limited. Stress hormones alter gut permeability and immune signaling, and altered sleep can change metabolic regulation. The gut is not just digestion, it is an ecosystem that talks to the brain and the immune system. In visuals, the ship's air ducts and the human intestine become parallel tunnels, both hosting unseen communities. A drifting microbiome is not a minor detail. It affects digestion, immunity, and mental health, and it can shift susceptibility to infection or inflammation. It also affects the microbial communities in air filters, water loops, and soil beds. The line between crew health and habitat health becomes blurred because the ship's microbes and the crew's microbes trade genes and niches. In deep time, the ship becomes a co-evolving environment, not a static container. Surgery is a special case that exposes the limits of autonomy. Major surgery requires sterile conditions, blood management, imaging, anesthesia, and trained teams, and each of those depends on equipment that must be maintained. In a small crew, expertise is scarce. In a crisis, the patient may be the expert, which is a scenario that reads like fiction until you run the staffing numbers. Even simple procedures are complicated by floating fluids, constrained space, and the need to control contamination. Even if you can perform surgery, you must manage complications. Infection control is harder in a closed environment where microbes circulate and surfaces are reused. Antibiotic resistance can evolve in isolated microbial ecosystems, especially if antibiotics are used repeatedly and imperfectly. A single outbreak can become a ship-wide event, because quarantine is limited by volume and by social necessity. The visual is claustrophobic: sealed doors, improvised isolation, and a crew that must keep working while avoiding one another. Blood is another constraint that hides behind the word medicine. Blood products have shelf lives, and refrigeration is energy. Donor compatibility is population limited, and anemia or clotting changes under microgravity complicate planning. Even a simple trauma protocol becomes a logistics problem when the hospital is also the habitat. A ship can carry tools, but it cannot easily carry time, and medicine often demands time. Drug shelf life becomes a quiet constraint that grows with time. Many medications degrade over years, especially under radiation and temperature cycling, and potency can drop below therapeutic thresholds. Resupply is impossible, and even communication with Earth cannot deliver a pill. Manufacturing drugs on board implies chemical plants, quality control, sterile packaging, and precursor supply chains. That is not a cabinet of supplies. It is an industry, and industries require trained people who must be replaced across generations. Unknown illnesses are the hardest category, because diagnosis depends on context and data. A ship is isolated from diverse pathogens, yet it is also isolated from diverse medical resources and specialist knowledge. A novel syndrome could emerge from radiation, stress, and altered physiology combined, and it might not resemble anything in textbooks. In deep time, the ship becomes its own epidemiological world. The question becomes unsettling. What does normal mean when your environment has never existed before? Psychology and social stability then become as critical as shielding thickness. Confinement compresses social life into a small volume, and the walls are always there. The view out a port can be magnificent, stars sharp as ice, the sun a hard coin, but the interior is routine. Monotony erodes attention and motivation, and attention is a safety system. In visuals, the same corridor repeats day after day, while the starfield outside never changes. Small conflicts can become structural when there is nowhere else to go. On Earth, distance is a pressure valve. In a ship, distance is scarce, and privacy is engineered rather than natural. Even sound becomes a factor, because fans and pumps create a constant acoustic bed that can irritate sleep and nerves. The habitat is not just a place. It is a stimulus field, and the nervous system lives inside it without escape. Long missions require governance that can survive leadership turnover. Rules must be legitimate, enforceable, and adaptable, because conditions change and emergencies happen. A ship cannot rely on Earth authority when messages take years, and even advice arrives too late to matter. The crew becomes a polity, whether it planned to or not. The constitution of the ship becomes part of life support. In visuals, a meeting table sits beside maintenance lockers, because politics and engineering share the same air. History offers uncomfortable parallels. Polar expeditions, submarine patrols, and early space stations all revealed how stress amplifies minor differences. The Antarctic winter-over experience, in particular, showed how isolation can distort time perception and magnify interpersonal friction. In those cases, the outside world remained reachable, even if slowly. In interstellar travel, the outside world is not reachable in any meaningful sense. That changes what accountability and trust mean, because there is no external referee. Purpose is a biological parameter, not a slogan. Motivation affects sleep, immune function, and compliance with exercise and maintenance routines. If the destination is a lifetime away, motivation must be inherited, not just chosen. That demands education, ritual, and a narrative that remains convincing across generations. Without that, compliance with maintenance and health regimes collapses, and collapse is contagious. The ship must teach meaning the way it teaches mathematics, patiently, repeatedly, and with consequences. Conflict is not only interpersonal, it can be ideological, generational, and resource-based, because values drift when environments are stable and isolated. In closed habitats, scarcity is felt immediately, because every buffer is finite and visible. A governance failure can become a life support failure, because sabotage can be as small as neglect. The most dangerous weapon may be apathy. In deep time, the enemy is not panic, but slow disengagement. Closed-loop life support is where biology and engineering fully merge. Water recycling must approach near total recovery, because losing even a small percentage per cycle becomes catastrophic over years. Air must be scrubbed of carbon dioxide and trace contaminants, including volatile organics from plastics and human metabolism. Oxygen must be regenerated reliably, without drifting chemistry that poisons catalysts or saturates filters. The system must also be monitored, because invisible failures are the ones that kill quietly. In visuals, the life support system is a cathedral of pipes and cartridges. Condensate drips into collectors, pumps hum, membrane separate, and sensors blink in quiet vigilance. Yet the true system includes the crew, because humans are part of the loop. Every breath is a chemical reaction, and every meal is a transfer of atoms that must be accounted for. Even a forgotten leak becomes a moral event, because waste is no longer abstract. Food production is not just calories, it is protein balance, micronutrients, essential fatty acids, and dietary variety that prevents deficiency and preserves morale. Monocultures are efficient but fragile, because a single pathogen or nutrient imbalance can wipe out the entire supply. Crop failure is not a bad harvest. It is a cascading health crisis that hits immune function, cognition, and social stability. The visuals can dwell on a single wilted tray of seedlings, because that tray represents weeks of future meals. Plants also behave differently under altered gravity and artificial lighting. Root orientation, water transport, and gas exchange can shift, and pollination may require human labour or engineered systems. The smell of soil and chlorophyll could become a precious sensory anchor, a reminder of Earth embedded in the ship. Yet that same soil is also a microbial reservoir that must be managed carefully. The farm bay is both sanctuary and risk, a green room that must be kept within tight parameters. A closed ecosystem must also close nutrient cycles. Nitrogen and phosphorus must be conserved, recovered, and reintroduced, because they are not optional elements. Waste streams must be processed without accumulating toxins, heavy metals, or persistent organics. Small inefficiencies compound over years into shortages or contamination, and the compounding is merciless because the system is finite. In visuals, a diagram of elemental loops overlays the ship, showing that civilization is chemistry with rules. Microbial ecology is the hidden engine of closed loops. Microbes purify water, process waste, and maintain soils, and many of the most useful organisms are invisible until they fail. They also form biofilms that clog pipes and corrode surfaces, and biofilms are stubborn because they are communities, not individuals. In a closed world, you cannot remove microbes. You can only manage them, guiding them like a gardener guides weeds. The ship becomes an ecosystem with valves, and ecology does not always respect valves. A biosphere in a can is hard because it is non-linear. Feedback loops amplify small errors, and delays hide problems until they are large. A slight shift in pH changes microbial communities, and that changes nutrient availability. That changes plant health, which changes oxygen production and carbon dioxide uptake. The system can drift into a new equilibrium that is incompatible with humans, even if every component still works. In deep time, stability is an active process, not a static achievement. Real experiments on Earth show how hard stability is. Sealed habitat projects revealed unexpected gas imbalances, microbial surprises, and psychological strain, even when the volume was large and the outside world was near. In some cases, oxygen levels fell as microbes and materials absorbed it, and crews had to intervene. A starship habitat is smaller, more stressed, and exposed to radiation. The margin for error is thinner, and the recovery options are fewer. The lesson is not that closed worlds are impossible, it is that they are alive and living systems drift. Reproduction and development in space is the most direct confrontation with deep time. If the trip is longer than a human lifespan, reproduction is not optional because the mission must become a lineage. Yet gestation under altered gravity is largely unknown, and unknowns in pregnancy are never abstract. Radiation exposure during development raises ethical and biological alarms because dividing cells are sensitive and mistakes echo through a lifetime. The ship must decide what risks it is willing to impose on people who did not choose the mission. Animal studies suggest risks to embryonic development under microgravity and radiation. Changes in implantation, organ formation, and vestibular development have been observed in various models, though translating them to humans is uncertain. Human data is limited and ethically constrained, because you cannot run full-scale experiments on children in dangerous conditions to validate a mission plan. The absence of evidence is not evidence of safety. In visuals, a nursery is framed not as comfort, but as a question posed to the future. Even if conception is possible, childhood development may be altered. Bone growth, vestibular calibration, and motor learning depend on gravity cues, and those cues shape how the brain builds its internal model of the body. A child raised in partial gravity may not tolerate full gravity at arrival, because muscles, bones, and reflexes may never have learned that world, the destination could be physically unreachable for the people who reach it. The irony is sharp. A successful voyage that delivers bodies unfit for the planet they sought. There is also the question of identity. If you're born on a ship, Earth is not home. The mission's origin story is history, and history can feel like mythology when it is not lived. What does arrival mean to someone whose entire life is the voyage, and whose friends, rivals, and ancestors are all inside the same hull? The biology of deep time is inseparable from the psychology of inheritance. In visuals, old photographs of Earth become relics, handled like sacred objects. Demography becomes a mission parameter, not a background statistic. Too few births and the population ages into collapse because skills and labour vanish faster than they can be replaced. Too many births and resources fail because food, water, and space are finite. Genetic diversity must be maintained to avoid inbreeding depression, which can increase disease risk and reduce fertility over generations. That implies a minimum population size and careful reproductive planning. The ship's census becomes as important as its fuel gauge. Reproductive governance is politically explosive because it touches autonomy and consent in the most intimate way. Yet a closed world cannot ignore it, because biology does not negotiate with ideals. The ship must choose between coercion, incentives, or technological mediation, and each choice carries conflict risk. A policy that stabilizes numbers can destabilize legitimacy, and legitimacy is a life support variable. The quiet question behind every rule is whether the next generation will accept it. So the ship becomes a world, not a vehicle. It needs hospitals, schools, farms, factories, and courts, because the functions of civilization cannot be outsourced across light years. It needs a maintenance culture where inspection is habitual and repair is honoured, because neglect is the natural enemy of closed systems. It needs institutional memory, because forgetting how a subsystem works can be fatal. Redundancy must exist not only in hardware, but in skills and roles. A starship is a machine that must also be a tradition. The visuals shift here from spacecraft to settlement. Corridors become streets, modules become neighbourhoods, and storage bays become granaries. A classroom exists beside an air scrubber, and a nursery exists beside a water processor, because everything is adjacent in a finite volume. The smell of cooking, the sound of tools, and the rhythm of shift changes become the weather of this artificial world. Through a window, the stars remain fixed, and that stillness becomes its own kind of landscape. By the time you make it self-sustaining, you have built a small civilization. That raises the uncomfortable question. If you can build a stable, closed civilization in space, why must it travel at all? Why not build many such worlds closer to home, where resupply and rescue remain possible? The answer, if there is one, is not purely technical. It is philosophical, and it is political. Perhaps the act of leaving is the point, or perhaps it is the cost of a story we refuse to abandon. Interstellar travel then stops looking like exploration and starts looking like diaspora. The goal shifts from reaching a star to preserving continuity, because the ship's primary achievement is survival through time. The mission is not a sprint to a destination. It is a long experiment in keeping a society coherent under permanent constraint. The star ahead becomes both a target and a story that keeps the system aligned. In visuals, the destination is a faint point on a navigation display, while the ship's interior is crowded with daily life. Earlier chapters showed how distance demands energy, and how speed turns space into a weapon. This chapter shows how time turns the crew into the fragile component. Biology is not a subsystem you can bolt on. It is the mission, because every other subsystem exists to serve living tissue. In deep time, the ship's most delicate machinery is not a gyroscope or a reactor. It is a human body. And that body is not a constant. It is a process, always changing. Even if future humans engineer themselves for radiation tolerance and altered gravity, the mission still lives inside time. Time changes bodies through aging, and it changes societies through drift, because values and institutions evolve even without external contact. The final barrier is not speed. The final barrier is continuity, the ability to remain the same project while everything inside the project changes. The ship must preserve not only oxygen and water, but intent. A starship can be designed to survive impacts and reject heat, and engineers can calculate margins with impressive confidence. It is harder to design a culture that survives boredom, grief and power struggles for centuries, because those are not linear forces. It is harder to guarantee that the people who arrive still share the mission's meaning, rather than treating it as a burden inherited without consent. Arrival might be triumph, or it might be mutiny delayed. The mystery is not whether the hull holds, but whether the story holds. So the prison of distance becomes a prison of deep time. The universe does not only separate stars by light years, it separates intentions by generations, because a plan is a fragile thing when it must be carried by children not yet born. The wall is not a single law of physics. It is the layered structure of reality, lived through fragile bodies inside a sealed world. The ship moves forward, but its people must also move forward, through biology, through memory, and through meaning. Next, we confront what time does to the project itself. When a journey lasts longer than institutions, the traveller is no longer a crew. The traveller is history, and history does not hold still. Even if future humans engineer themselves for radiation tolerance and altered gravity, the mission still lives inside time. The last barrier is not a stronger hull or smarter fuel, because those can be iterated and tested under controlled conditions. The last barrier is that civilizations do not stay still long enough. Interstellar distance converts into duration, unless you pay the relativistic price, an accounting that is both physical and social. At non-relativistic speeds, a few light years becomes a lifetime, and a few dozen light years becomes a historical era. Even at a steady 1% of light speed, a 10 light-year crossing is 1,000 years of travel. For most reachable targets, practical speeds still mean decades to centuries of travel, even if propulsion is efficient and continuous. That duration is longer than careers, longer than governments, longer than stable economic regimes. When engineers talk about delta V, they describe how much velocity change a vehicle can buy with propellant and energy. Behind the shorthand is the rocket equation, which punishes mass and rewards exhaust velocity with an almost moral severity. When historians talk about revolutions, they describe how quickly institutions can change their rules, their leaders, and their sense of legitimacy. A star mission must survive both kinds of accounting, because it spends momentum and meaning at the same time. A space agency can plan for 10 years and still struggle to hold funding through budget cycles and shifting priorities. A corporation can plan for a quarter and still struggle to hold attention through market shocks and leadership turnover. A nation can plan for a generation and still be rewritten by elections, crises, and war. Sometimes without a single shot fired, even a stable democracy can change course through committees, courts, and quiet, bureaucratic edits. We treat a star mission like a project with milestones and deliverables, as if it were a bridge or a telescope. Time treats it like a lineage problem with inheritance and drift, where each generation edits the mission by living it. The ship does not only cross space, it crosses the churn rate of human institutions. Start with the launch civilization, because it sets the mission's meaning as much as it sets the mission's hardware. It chooses the destination, the propulsion architecture, and the rules for the crew, but it also chooses the story that justifies the cost. That story is a political instrument and a psychological scaffold, because it must translate mass, energy, and risk into purpose. It must also survive scrutiny from people who did not vote for it. Visually, imagine a launch ceremony under floodlights, with banners and speeches echoing in a cavernous hangar. The ship's skin gleams like a new coin, and frost curls off cryogenic lines like breath in winter. Cameras pan across faces that are certain they are witnessing a clean beginning. In that moment, the mission feels like a single decision, clean and final, as if history has been pinned to a date. Now stretch that story across a century, and the clean edges begin to blur. Languages shift, slang becomes grammar, and grammar becomes foreign, even when the alphabet stays the same. Values shift, and what once sounded heroic can later sound like theft or like vanity, or like a crime disguised as destiny. Even the word progress can become suspicious, depending on what it has cost. A mission charter is a document written in one moral climate, with assumptions that feel invisible to its authors. A century later, that climate may be unrecognizable to the people living inside the ship, who inherit the text but not the context. The plan survives only if it remains legitimate under new eyes, and legitimacy is a moving target. What happens when the charter's most sacred clause reads like an old mistake? Even if Earth remains stable, the ship becomes its own society through simple isolation and delayed feedback. It cannot be managed like a remote station when messages take years and replies return to a different political era. It cannot be corrected like a colony when rescue is impossible and replacement crews cannot arrive. The ship is not a branch office. It is an island that cannot see the mainland. So the engineering problem turns into governance, because governance is what keeps a closed world coherent. A generational ship must carry law, education, and conflict resolution as core subsystems, just as surely as it carries air revitalization and thermal control. These are not decorative institutions for morale. If they fail, propulsion and shielding become irrelevant, because the ship will fail from the inside. Generational ships begin with a simple premise that becomes unsettling when spoken aloud. If the trip outlasts a human lifespan, the crew must reproduce and train successors, and the mission becomes hereditary. The voyage becomes a multi-century civilization compressed into a moving habitat, with birth, aging, and death occurring under the same ceiling. The ship becomes a town that cannot stop moving. That premise creates an immediate ethical fracture that cannot be welded shut by optimism. The first crew can consent to risk and confinement, because they can compare the mission to the life they might have lived. The later generations cannot consent to being born into the mission, because the mission is the only world they will ever know. They inherit the consequences before they inherit the language to describe them. A child born on the ship inherits constraints as facts of nature, long before they can name them. The hull is the sky, the rules are the weather, and the destination is a rumour carried by lessons and ceremonies. The mission asks them to sacrifice for a choice they never made, and to treat that sacrifice as normal. How do you teach freedom in a place where outside is vacuum? Every governance model must answer that tension, even if it tries to hide it behind procedure. Is the mission a contract, a constitution, or a religion? And what happens when those categories collide? Does it allow exit when there is nowhere to go? And what does exit even mean in a closed ecosystem? A door can be symbolic, yet symbols still have consequences. Some designs imagine strict hierarchy, because ships need discipline when a single mistake can cascade. Others imagine democracy, because legitimacy needs voice when coercion becomes corrosive over decades. Both face the same physics, because closed worlds amplify conflict and remove the safety valve of distance. A ship is a pressure vessel for society as well as for air. Hierarchy can maintain order, yet it risks tyranny and revolt when authority becomes hereditary or self-protecting. Democracy can maintain legitimacy, yet it risks paralysis under emergency when debate consumes the time needed for action. A ship needs decisions that are both accepted and fast, and it needs a way to recover when decisions are wrong. Recovery is not forgiveness alone, because recovery must restore function. Law on a starship cannot be an abstract ideal floating above daily life. Law is life support, because sabotage and neglect are existential threats, not merely moral failures. A broken pump is not an inconvenience. It is a countdown measured in oxygen, partial pressure, and carbon dioxide rise. In a sealed habitat, the margin between fine and fatal can be a few percentage points. In a sealed habitat, the atmosphere is a managed chemical mixture, not an infinite commons. Carbon dioxide scrubbing depends on sorbents and regeneration cycles, and oxygen production depends on electrolysis, stored reserves, or bioregenerative systems. Trace contaminants matter too, because plastics outgaze and microbes metabolize, and both alter the air invisibly. Water is reclaimed through filtration, distillation, and microbial control, and each step is vulnerable to contamination. When people argue about rules, they are arguing about the stability of these loops. Education becomes another life support loop because skills must be transmitted across generations with near zero loss. The ship must teach engineering, medicine, agriculture, and governance as survival crafts, not as elective interests. It must also teach the reasoning behind procedures, because rote compliance collapses when stress tests the system. A checklist works best when the mind behind it understands why it exists. That education cannot be optional, because specialization is fragile in small populations. If one generation fails to produce enough technicians, the ship loses repair capacity, and the loss may not show immediately. The failure can be delayed, then sudden, when a rare fault appears and no one remembers how to diagnose it. The ship can look healthy right up until the day it cannot be fixed. Institutional memory must be engineered like redundancy, with multiple formats and overlapping custodians. Manuals must remain readable as language evolves, and diagrams must remain interpretable as symbols drift. The ship may need controlled vocabularies, standardized iconography, and periodic rewrites that preserve meaning while updating form. Training must remain effective as culture changes, because culture shapes what people notice and what they ignore. Even the meaning of competence drifts, because competence is partly technical and partly social. A society can become brilliant at maintaining what it already has, and it can also become suspicious of systems it does not understand. Over time, expertise can look like privilege, and privilege can look like threat. The same person who keeps the air clean can be accused of hoarding power. This is mission drift in its pure form, where adaptation becomes divergence without anyone intending betrayal. The ship's culture adapts to its environment, not to the launch plan, because the environment is what selects behaviours. Over time, the environment is the ship itself, with its routines and its constraints. Selection does not ask what the founders wanted. Selection asks what survives. A closed world selects for different virtues than a frontier, and the selection pressure is constant. It rewards conformity, maintenance discipline, and risk aversion, because stability is a daily victory. It punishes experimentation that threatens stability, even when that experimentation might prevent future failure. The paradox is that safety today can purchase fragility tomorrow, yet the mission also needs innovation, because failures will be novel and wear will be uneven. Radiation embrittles materials, lubricants break down, seals creep, and electronics accumulate damage even behind shielding. The ship must repair what was never designed to be repaired, using tools that were never meant for that job. It must improvise without a supply chain, and it must do so while keeping the lights on. So the ship must balance two instincts that fight each other, and the fight never ends. It must be conservative enough to avoid catastrophe, because catastrophe has no outside help. It must be flexible enough to survive surprises, because surprises are guaranteed over centuries. That balance is not a technical setting you can lock behind a panel. It is a cultural trait that must persist for centuries, and culture is not a fixed parameter. Culture is a living system that mutates under stress, under boredom, and under power. Even the rituals meant to preserve meaning can become hollow, then contested, then repurposed. What begins as stewardship can end as theatre. Consider language again, because it is a simple demonstration that requires no speculation. In a few centuries, English becomes multiple Englishes, separated by geography and media even on Earth. In a millennium, it becomes something else, with familiar roots and unfamiliar meanings. On a ship, the separation is sharper, because there is no fresh influx of speakers. Technical vocabulary can be preserved by schooling, yet everyday speech will still drift, and drift changes thought. It changes how people think about authority and obligation, because words carry hidden assumptions. It changes how they interpret the mission's original texts, especially when those texts become ceremonial rather than practical. A phrase once meant as guidance can harden into a slogan. Religions and ideologies can stabilize meaning, yet they also transform it, because interpretation is a form of power. A mission story can become sacred, then contested, then weaponized in factional struggles. It can become a tool for unity, and then a tool for control. The same myth can comfort one generation and imprison the next. The ship also carries class structure, because roles matter and scarcity makes roles visible. Engineers control the systems that keep everyone alive, and medics control the boundary between illness and death. That creates leverage, even if the society denies it, and even if the leverage is exercised with good intentions. On a small ship, informal status can be as decisive as written law. Resource allocation becomes politics in its raw form, because every resource has an opportunity cost. Space, privacy, food variety, and reproductive permissions become contested goods, and the contest never fully disappears. Even noise levels and light schedules can become political, because they shape sleep and mental health. In a closed world, inequality is always visible, because there is no elsewhere to hide it. The launch planners can write rules to prevent this, with quotas, rotations, and oversight councils. Rules do not prevent drift when incentives change, and incentives always change as people adapt to constraints. Over centuries, enforcement becomes interpretation, and interpretation becomes power, and power becomes tradition. Tradition can be gentle, yet it can also be a locked door. Now add the psychological weight of deep time, which is different from ordinary hardship. The destination is not a place you will see. It is a promise you must maintain for your grandchildren's grandchildren, while your own life remains bounded by the same corridors. The mind can endure pain with an endpoint. It struggles with endurance that has no personal conclusion. A mission can survive boredom for a year, because novelty and urgency can be manufactured. It struggles to survive boredom for a century, because routine becomes the dominant experience. Routine erodes urgency, and urgency is what turns maintenance from a chore into a duty. When urgency erodes, maintenance becomes performative, and performance is a dangerous substitute for care. Checks become shortcuts, and shortcuts become normal, and normal becomes invisible. Normal is the most dangerous word on a starship because it hides slow decay behind familiarity. A filter that is usually fine is a filter that will fail when the schedule slips. A valve that is always stiff is a valve that is already warning you. In the visuals, we move through the ship's maintenance bays, where panels are opened and closed with practiced motions. A technician signs off on a checklist while a child watches, learning that the ritual matters even if the reason feels distant. Somewhere deeper, pumps hum with the steady confidence of machines that have not yet failed. The camera lingers on worn handholds polished by generations. The ship can try to preserve urgency through ritual, because ritual is a technology for memory. It can celebrate launch anniversaries and teach the destination as identity, turning navigation charts into icons. It can frame the mission as purpose, and purpose can be a powerful stabilizer. Yet purpose works until it competes with lived reality, because lived reality is immediate and persuasive. If the ship is stable and self-contained, the destination can feel unnecessary, like a story told by ancestors. The ship can start to feel like home, and home is a rival to any promised land. That is the paradox of success, and it is not merely philosophical. The better the ship becomes as a habitat, the less compelling arrival becomes because arrival is risk. The mission can be outcompeted by comfort, and comfort can be rational in a universe that punishes mistakes. So the arrival problem emerges long before arrival as a slow shift in motivation rather than a sudden mutiny. What does it mean to arrive if the society no longer wants to? What does it mean to arrive if the society no longer agrees on why? Arrival is not a single moment with a flag and a speech. It is a decision made by a culture that may not share the launch culture's goals, and that culture must live with the consequences. The ship can reach the target star and still refuse to land because refusal may look like prudence. In a closed world, prudence can be indistinguishable from surrender. The ship can also arrive with knowledge that is obsolete, even if its people are intelligent and diligent. A multi-century voyage freezes a technical stack in time, preserving tools, software, and assumptions from an earlier era. It carries design philosophies that may have been superseded on Earth, and it cannot simply download the future. Even file formats and programming languages can become archaeological layers. Even if the ship can manufacture parts, it cannot easily reinvent its entire technology base. Reinvention requires research ecosystems, surplus resources, and tolerance for failure, because learning is expensive. A starship has little surplus, and failure can be fatal, so experimentation becomes politically fraught. The society may know what it lacks, yet still be unable to afford the path to regain it. So the ship becomes a museum that must also function, and that dual identity shapes its culture. It preserves old solutions because they are proven, and proof is comforting in a closed world. It risks being trapped by them, because the cost of change is paid in risk. The museum is not nostalgic, it is defensive. This is where technological obsolescence becomes existential, not just embarrassing. A slow ship launched today can be overtaken by a faster ship launched later, and the overtaking is not symbolic. The first crew becomes a sacrifice to a better future, watching their own mission become a historical footnote. The sky can contain two ships headed to the same star, and only one will be remembered. The intuition is simple and cruel, and it has haunted interstellar planning for decades. Propulsion improves over time, so waiting can reduce travel time more than launching now, at least for a while. There is a point where the best strategy is delay, because the future buys speed. The question becomes not can we go, but when does going stop being premature? This is the weight equation logic, often discussed in sober studies rather than in popular dreams. If technology growth is fast enough, the optimal launch date moves forward, and early launches become suboptimal by definition. Early launches risk becoming the wrong generation of ship, not because they fail, but because they succeed too slowly. The mission can be punished for being first. Historically, this resembles other moments when technology outran commitment, from sailing ships replaced by steam to early aircraft surpassed within a decade. It also echoes polar expeditions and long-sea voyages, where communication delays and supply limits turned planning into fate. Yet interstellar travel magnifies the effect, because the timeline is long enough for multiple revolutions to occur mid-voyage. The ship departs under one technological worldview and arrives under another, or arrives to find that others arrived first. That discourages commitment, because commitment locks you into a long timeline that cannot be renegotiated. Investors, governments, and publics prefer projects that finish within their own political horizon, where credit and blame remain legible. Interstellar missions do not, and that mismatch is itself a barrier. The mission asks a civilization to care about outcomes it cannot personally witness. Even a civilization that wants the stars must choose between two failures, and neither feels heroic. Launch early and risk being overtaken and forgotten, becoming a drifting monument to impatience. Wait longer and risk never launching at all, because later can become a permanent excuse. The hardest enemy is the calendar that always offers another year. Obsolescence also attacks the ship internally, in ways that are quieter but more relentless. Components age, standards change, and expertise becomes harder to renew when the original designers are long dead. The ship must keep ancient systems running without external industry, and it must do so while its own tools wear down. Even reference instruments drift, and drift is the enemy of precision. That brings the supply chain problem into focus, because Earth's resilience is partly distributed. On Earth, complex machines survive because parts and specialists exist elsewhere, and because industries cross-support each other. A starship has no elsewhere, and the absence of elsewhere turns minor failures into existential ones. A cracked bearing is not a purchase order, it is a crisis meeting. Any critical failure is final if it exceeds onboard capability, and onboard capability is bounded by mass and energy. There is no rescue mission that arrives in time, because even a near-light speed rescue would still be late. There is no spare parts economy that can scale with unexpected demand, because there is no market and no shipping lane. The ship must be its own warehouse, its own clinic, and its own machine shop. So the ship must carry an industrial stack or accept fragility, and both choices are costly. It must have fabrication, materials processing, diagnostics, and quality control, and it must have the energy and feedstocks to run them. It must also have the knowledge to rebuild those capabilities after accidents, because accidents are inevitable. A fire in a workshop is not just damage, it is lost capacity. Carrying an industrial stack increases mass and complexity, and mass is the enemy of acceleration. Complexity increases failure modes and maintenance burden, because every subsystem becomes another thing that can break. The ship becomes heavier, slower, and more dependent on its own perfection, which is an uncomfortable dependency. It is a civilization forced to be self-sufficient before it has even arrived. If the ship does not carry that stack, it becomes a brittle artifact, impressive but unforgiving. It can survive only if nothing important breaks, and the probability of nothing important breaking falls with time. Over centuries, that is not a plan. It is a gamble disguised as a schedule. This is a reversibility as a design condition, and it changes the philosophy of engineering. Many failures in spaceflight are survivable because help exists, and because spare capacity can be shipped later. In interstellar space, survivability must be internal, and internal survivability must be planned as if the ship were the last factory in the universe. Redundancy becomes culture, not just hardware. Even if you can print parts, you must print the printers, and then you must print the tools that maintain the printers. You must maintain machine tools, calibration standards, and measurement instruments, because precision drifts with wear and temperature cycles. Metrology is not glamorous, yet it is the foundation of reliable repair. Precision is a civilization, not a gadget, and civilization is heavy. Now consider communication, because it shapes identity and control more than any speech ever could. At a few light years, messages take years, and even that delay changes the texture of conversation. At tens of light years, they take decades, and decades turn dialogue into archive. A question asked in youth can be answered after retirement or after death. Communication becomes a one-way time capsule, because advice arrives after circumstances have changed. Earth can send guidance, yet the situation has already shifted through accidents, births, and political changes. The ship can reply, yet Earth has already moved on, and the reply lands in a different world. The exchange resembles letters found in an attic, intimate but out of time. This creates asynchronous civilizations, like two clocks that began together and then drifted apart. The ship lives in a delayed conversation with a past that cannot respond, and that past becomes strangely authoritative. Earth becomes a mythic origin, not a manager, and origin stories are powerful precisely because they cannot be corrected. The ship can argue with Earth, yet only with Earth's echo. Even if Earth tries to govern, enforcement is impossible, and impossibility changes behavior. Authority requires timely feedback and credible consequences, and light speed delay removes both. A command that arrives years late is not a command. It is a suggestion from ghosts. The ship's culture will therefore treat Earth messages as literature, even when they are written as policy. They will be studied, argued over, and reinterpreted through local needs and local power. They will not be obeyed like orders, because obedience requires a shared present. The same paragraph can be cited as law by one faction and as warning by another. The same delay applies to scientific knowledge, which means the ship and Earth become each other's fossils. Earth's discoveries arrive late, and the ship's discoveries arrive late, and each side reads the other as history. Over time, the ship and Earth diverge like separated species, sharing ancestry but not sharing now. The gap is not just information, it is lived experience. Shared present is what makes a civilization coherent, because coherence depends on synchronized expectations. When synchronization fails, myths fill the gaps, and myths can stabilize or destabilize depending on who tells them. The ship may romanticize Earth as paradise or condemn it as abandonment, and either story can become political fuel. The truth may be irrelevant if it arrives too late to matter. Now widen the frame to the target itself, because the destination is not a fixed dot on a map. Stars move, systems evolve, and gravitational tides reshape trajectories even when nothing dramatic happens. The night sky looks permanent to human eyes, but it is a slow choreography measured in millennia. Proper motion is small each year, yet it accumulates like compound interest. Navigation across decades is prediction, not steering, because the ship cannot make large course corrections cheaply. You launch toward where a star will be, not where it is now, and you commit to a forecast. You plan for perturbations you cannot fully measure, because the interstellar medium is not uniform. Even sparse gas and dust can sandblast at high speed, turning tiny grains into bullets. Binary stars shift relative positions, and planets migrate within disks over long times, changing what arrival means. Dust clouds and local medium density vary, changing hazard and drag, and even a thin gas becomes relevant over decades. The route is a forecast, and forecasts have error bars. Those error bars become governance questions, because someone must choose how much risk to accept. Even if the target system is stable, the sky is not, because the galaxy is in motion. The Sun and nearby stars orbit the galactic center, and their relative geometry changes, turning constellations into temporary patterns. The mission crosses a moving lattice, where the endpoints slide while you travel. The map is alive, and the ship must trust its instruments more than its inherited star law. This does not make navigation impossible in principle, because physics remains consistent and measurement improves. It makes it another layer of uncertainty that compounds with time, like interest on a loan. Every decade adds more unknowns, and unknowns become decisions that must be made without complete information. The ship's planners can reduce uncertainty, yet they cannot delete it. Now return to the arrival problem with this cosmic context, because arrival is not simply reaching a coordinate. Arrival is meeting a system that may not match the launch assumptions, because assumptions age. A planet that looked promising may be hostile on closer inspection, and promising may have been defined by outdated biology. Even the definition of habitable can shift as the ship's culture changes. A habitable zone world may be tidally locked, airless, or chemically incompatible with Earth life, even if it reflects the right amount of starlight. Its atmosphere might be rich in carbon dioxide, or its surface might be sterilized by flares, or its oceans might be hidden under ice. The ship must adapt or abandon, and adaptation requires resources. Resources require consensus, and consensus is never guaranteed. If the ship cannot adapt, then arrival becomes a crisis rather than a celebration. The society must decide whether to settle, to continue, or to stop, and each option carries moral weight. Those choices can fracture legitimacy because factions will argue that the mission's meaning has been betrayed or fulfilled. The star can be reached, yet the promise can still fail. Arrival can also be abandonment in a quieter sense, where no one declares mutiny and no one tears down symbols. The ship reaches the star, then chooses to remain in space, building habitats in orbit and mining local asteroids. It becomes a permanent habitat orbiting a new sun because space is safer than an unknown surface. The new system becomes a resource base rather than a homeland. In that case, the destination was never a planet in the way the launch posters implied. The destination was the ship itself, refined and expanded, because it was the only reliably habitable world in the plane. The new star becomes a power source and a landscape, not a home. The mission's last act is to admit what it has been all along. This is the emerging answer of this chapter, and it is both practical and unsettling. Interstellar travel demands not a vehicle but a self-contained, multi-century civilization with all the fragility that implies. The ship is the destination because it must be, and because the only constant is the habitat you carry. The engines matter, yet the culture matters more. That answer changes the meaning of the central question, shifting it from engines to identity. We asked what barrier makes interstellar travel impossible for humans. The barrier is that the trip requires a civilization that can survive itself, including its own boredom, its own politics, and its own reinterpretations. It requires continuity without stagnation, and adaptation without collapse. Engineering can be solved with enough energy and enough mass, at least in principle, and with enough time. Biology can be managed with enough shielding and enough habitat design, even if the solutions are heavy. Time attacks the one thing that cannot be machined, because it lives inside minds and institutions. Time attacks continuity of intent, and it does so without malice through ordinary change. It attacks legitimacy, motivation, and shared meaning, and it attacks the assumption that the people who arrive are the same project that launched. A starship can preserve atoms better than it can preserve purpose. It can recycle water and air with high efficiency, closing loops until loss rates become tiny. It cannot recycle consent, because consent is personal and time-bound. It cannot guarantee that future people will accept the debts their ancestors incurred, so the tension becomes existential, and it does not resolve with better engineering alone. The launch civilization and the arrival civilization may be strangers, separated by experience and by moral vocabulary. One may not exist when the other is born, and absence changes what promises mean. Earth might collapse, transform, or simply lose interest, and any of those outcomes breaks the narrative thread. The ship might fracture, reform, or abandon the mission, and those outcomes may be rational from inside the hull. The crossing is not one risk. It is a century of risks, layered and interacting. This is why interstellar travel feels like a prison even when the stars look close, because the confinement is temporal as much as spatial. The prison bars are not only distance and energy. The bars are time and social instability, and the lock is the absence of rescue. The ship is free to move, yet trapped in consequence. If you want a mission that survives centuries, you must build a culture that treats maintenance as sacred, not merely important. You must build institutions that can evolve without losing function, like organisms that change shape while keeping their organs working. You must build legitimacy that can survive drift, because drift is guaranteed. The mission must be re-argued, retaught, and re-earned. That is not a spacecraft program with a finish line and a ribbon cutting. That is a founding of a new society under permanent constraint, where every generation must renegotiate its relationship to the mission. It is an architecture of time, built from rules, stories, and the quiet labour of keeping systems alive. The most heroic act may be the least cinematic one, doing the same careful task correctly for a lifetime. Now zoom out one last time. Human time is already a barrier, yet cosmic time is larger and quieter, and it does not care about our charters. The universe itself evolves, and it imposes limits that no culture can vote away. From here, the story moves beyond the ship and its people, and into expansion, horizons, and the large-scale structure of the universe. The final limit is not dramatic, because it does not arrive with explosions or villains. It is patient, written into geometry. It is the quiet geometry of space-time, where distance grows, light cones narrow, and reachable space shrinks with time. The last chapter follows that geometry to its end and asks what it means to live in a universe that slowly closes its doors. Now zoom out one last time, from human time to cosmic time, where expansion, horizons, and geometry impose the final, quiet limit. Across these chapters, we chased a single wall, hiding behind many smaller walls, and each one looked negotiable until it wasn't. We asked what makes interstellar travel effectively impossible for humans, even with far future technology and heroic engineering. The answer is not one missing invention, but a compounded architecture of space-time, energy, hazard, biology, and time. First, we must reframe the word impossible, because physics uses it precisely and without mercy. Some things are forbidden by the structure of relativity, because faster than light breaks causality and lets effects arrive before causes. Other things are allowed in principle, yet become effectively impossible at human scales, because the costs grow faster than capability. Interstellar travel lives in that second category, until the costs stack into something that behaves like the first. Each barrier alone can be argued with optimism, budgets, and cleverness, especially in a design meeting. Put them together and they multiply, because every solution adds mass, power, complexity, and time. Relativity sets the basic geometry of the problem, and it never relaxes, not even for perfect engines. Light speed is not a speed limit sign. It is the slope of causality in space-time, the angle that defines what can influence what. In Minkowski space, your future is a cone, and anything outside it is not far, it is unreachable in time. Even when you travel near light speed, distance does not vanish. It becomes a trade between frames. The traveller can compress proper time, but the outside universe still measures the full separation, and that separation is enforced by light cones. A star is not simply a point on a map, it is a point on a timeline. Energy is the next gate, because high speed demands a non-linear payment that feels almost designed to discourage ambition. Kinetic energy rises with gamma, and the curve steepens as you approach c, turning incremental speed into exponential cost. In plain terms, the last few percent toward light speed costs more than everything before it. Whatever you spend to accelerate, you must spend again to brake, unless you accept a flyby as your only arrival. That second payment is easy to forget in concept art, yet it dominates real mission design. A meaningful arrival means matching velocities, not merely passing through a system like a bullet. The rocket equation tightens the vice, because propellant is not just fuel, it is mass you must carry and accelerate. Even with high exhaust velocity, carrying reaction mass multiplies the initial mass, which multiplies the energy, which multiplies the heat. Every kilogram of just in case becomes a kilogram you must pay for twice. Then the interstellar medium turns speed into exposure, and exposure into risk that cannot be fully engineered away. Sparse gas becomes a particle beam in your frame, and dust becomes shrapnel with catastrophic tail risk. At relativistic speeds, even a grain can deliver energy comparable to explosives, concentrated into a microscopic impact. Shielding can reduce risk, yet shielding adds mass, and mass raises the energy bill that forced the speed in the first place. A forward shield thick enough to matter is not a cosmetic bumper, it is a structural organ of the ship. It must absorb impacts, spread heat, and survive erosion for years without replacement. Cosmic rays add a quieter hazard, because they are not a single threat but a spectrum of particles and energies. High-energy nuclei can punch through materials, creating showers of secondary radiation inside the habitat. The more shielding you add, the more carefully you must choose it, because some materials can worsen the dose by producing those secondaries. Thermodynamics closes the loop, because power becomes heat, and heat must be rejected into space. In vacuum there is no convection, so radiators must shine their waste away as infrared light. Radiators scale with waste heat, and waste heat scales with the very systems that keep you alive and moving. You can hide a ship in darkness, but you cannot hide entropy, because the universe demands an infrared receipt. The hotter your radiators, the smaller they can be, yet higher temperature stresses materials and increases detectability. The colder your radiators, the larger they must grow, becoming fragile wings that invite damage. Biology adds a different kind of limit, because humans are not tolerant of deep time in closed boxes. Closed habitats drift, microbiomes evolve, drugs degrade, and rare medical events become inevitable over decades. A small failure rate per year becomes a certainty over a century, even if everything is reliable. Artificial gravity might help, yet it demands large rotating structures that must stay balanced, repairable, and safe for generations. Rotation introduces bearings, seals, vibration and fatigue, and it turns minor mass shifts into stability problems. A habitat ring is not just a room, it is a machine that must never stop being a machine. Even psychology becomes engineering because isolation is not a mood, it is a chronic condition with feedback loops. The crew's world would be measured in cubic meters, routines, and the same faces year after year. What does home mean when every horizon is metal and every sunrise is scheduled? Civilization is the final local layer, because missions longer than institutions become inheritance problems. A crew becomes a polity, and a plan becomes a myth that must stay legitimate across births and funerals. Even if hardware survives, continuity of intent can fail through boredom, conflict, and rational redefinition of success. History gives us a faint echo of this, because long projects on Earth already strain continuity. Cathedrals took centuries, dynasties rose and fell, and even written instructions drifted in meaning as language shifted. If that happens on a planet with resupply, what happens in a ship with no outside correction? So far, the story has been human scale, where stars feel like distant islands across a black sea. Now we widen to the universe itself, because the largest map has edges that are not drawn by us. The universe expands, and that expansion is not galaxies flying through space like shrapnel. It is space itself stretching, carrying distant galaxies away with time. On small scales, gravity winds and binds systems together, stitching matter into stable neighborhoods. The Milky Way does not expand in any meaningful way, and neither does the local group because their gravity overwhelms the cosmic stretching. Yet on the larger scales, expansion dominates, and it changes what is reachable even in principle. Modern cosmology learned this in steps, from Hubble's redshifts to the later discovery that expansion is accelerating. That acceleration is inferred from standard candles like Type Ia supernovae, whose brightness reveals distance and whose redshift reveals recession. The result is unsettling. The far universe is not merely expanding, it is slipping away faster with time. To make this accessible, imagine light as a messenger trying to cross a growing field of tall grass. If the field stretches fast enough, the messenger can run forever and still never arrive, because the ground itself lengthens. That is the intuition behind a cosmic event horizon, a boundary beyond which signals sent now will never reach us. This is not a technological failure, and it is not a temporary condition that better engines can outwait. It is a geometric fact of an expanding spacetime with accelerating expansion, encoded in the metric itself. Some regions of the universe are already causally disconnected from our future, even if we wait forever. The night sky hides this because we see the past, not the present, and the past can be more connected than the future. Light from distant galaxies began its trip when the universe was smaller, and it arrives as a historical record. As time passes, more galaxies cross the horizon, and their last photons become the final pages of a book. Visually, this is a slow dimming, not a sudden blackout, as wavelengths stretch and energy thins. A galaxy does not vanish like a lamp switching off. It reddens, fades, and becomes harder to distinguish from the background. Eventually, the information is still out there, but no longer deliverable to us. So the ultimate context is hauntingly simple. There is a maximum sphere of influence for any observer, and it can shrink in practical terms as expansion accelerates. The universe does not only separate objects by distance, it separates them by forever. It would be easy to think this makes the Milky Way irrelevant, yet the same theme repeats locally in a more familiar key. Inside our galaxy, expansion is negligible, but causality is still enforced by light cones and finite signal speed. A star 10,000 light-years away is not far in a cosmic sense, yet it is separated by 10,000 years of delay. That delay is not just a communication inconvenience, it is a coordination killer that changes the meaning of action. A conversation becomes an archive, and a rescue becomes impossible by definition, because help cannot outrun the clock. Even if you could travel fast, the galaxy is still a place where help arrives too late, because the map is drawn in time. This is where the earlier chapters converge into one conclusion, like threads pulled into a knot. The real barrier is not distance alone, because distance can be crossed slowly if you accept the consequences. The real barrier is the price of crossing quickly enough to matter, while keeping humans alive, sane, and continuous. Consider the full accounting in one breath, because this is the wall. You need energy to accelerate a massive ship, and energy again to decelerate into a meaningful arrival. You need shielding mass against dust, gas, cosmic rays, and a blue-shifted radiation headwind. You need life support that stays stable for decades, then for generations if the trip is longer. You need heat rejection for propulsion, computing, habitat systems, and radiation shelters, because every watt becomes a thermal problem. You need redundancy, repair capacity, and an onboard industry, because there is no supply chain. You need governance that prevents sabotage and neglect, and education that preserves technical competence without loss. You need a culture that treats maintenance as sacred, because small errors compound into fatal drift. You need motivation that survives the fact that most travellers will never see the destination. Any one of these can be imagined as solvable with enough time and resources, especially on a whiteboard. Together they form a coupled system where solving one worsens another, and the feedback is relentless. More shielding increases mass, which increases energy, which increases heat, which increases radiator area, which increases vulnerability. This is why the documentary's hook lands with weight, even when the stars look close in a telescope. The universe looks like an ocean of stars, but it behaves like a prison of distance, time, and physics. The bars are not made of metal, they are made of compounding constraints. At this point, time dilation often enters as a supposed escape hatch, offered as if it were a loophole. Relativity can compress proper time for travellers at high gamma, making a long trip feel shorter on board. That effect is real, measurable, and beautifully consistent with experiment, yet it does not save human civilization, and it does not erase the cost. To get large time dilation, you must approach C, and the energy curve punishes you for it. The hazards also rise because the interstellar medium becomes more lethal with speed, and the CMB becomes a forward radiation field. In your frame, that microwave background is no longer a gentle bath, it is a concentrated headwind. The ship becomes a particle physics experiment that must also be a home, and those demands fight each other. You want thin structures for mass efficiency, yet you want thick structures for radiation and impact tolerance. You want high power for propulsion, yet you want low waste heat for survivability and stealth. Even if the crew experiences years while Earth experiences centuries, Earth's timeline still advances without them. Institutions change, languages drift, and the social contract between ship and origin dissolves into legend. Time dilation can separate travellers from their own civilization more efficiently, but separation is the very problem. So the central question becomes sharper, and it stops sounding like science fiction and starts sounding like accounting. What is the fundamental, non-negotiable barrier that makes practical interstellar travel effectively impossible for humans? It is the layered structure of space-time causality, paid for in relativistic energy and thermodynamics, amplified by environmental hazard, and lived through fragile biology and unstable civilization. This does not mean exploration ends. It means it changes form. Interstellar travel may become probes that do not need air, sleep, or consent, and that can accept one-way missions without tragedy. It may become AI emissaries that can wait centuries without boredom, and can tolerate radiation with redundancy. It may become machines designed for repair by other machines, patient and indifferent to delay. It may become beamed data and remote presence, where we explore by sending instruments and receiving information. The bandwidth can be high, yet the latency remains, and latency changes everything about control. When commands take years to arrive, autonomy is not a feature, it is the mission. It may become slow communication with long delays, where the exchange is more like archaeology than conversation. You send a question, and the answer returns to a world that has already moved on. What does diplomacy mean when every message is a time capsule? It may become a network of local habitats and solar system scale expansion, because the nearest resources are still vast. In our own system, energy from the sun is abundant, and materials in asteroids and moons are immense. The frontier may be wide without ever needing another star. For humans, the practical future may be a layered approach that respects the gradients of risk. Fast, light probes go outward, while heavy living systems stay closer to rescue and resupply. The dream shifts from migration to measurement, from planting flags to building understanding. This is not a defeat, it is a clarification of what the universe is offering and what it is not. The universe does not negotiate with our desires, because laws are not policies and exceptions are not granted. Yet it does reveal, and revelation is a kind of gift, because limits are part of the map. The stars remain real, and the longing remains real, but the path is not a road. It is a boundary condition written into geometry, energy, and time, and it holds whether we like it or not. Interstellar travel fails not because we lack a clever engine, but because the universe charges a compounding price that humans cannot sustainably pay. So the haunting conclusion is also a clean answer, the kind science prefers when it can get it. The real barrier is the combined architecture of space-time expansion, light-speed causality, and thermodynamic cost, amplified by the fragility of bodies and the drift of civilizations. The ocean of stars is visible, but the prison is the rules that connect visibility to reachability, and in that recognition, exploration becomes something quieter and more honest, like listening instead of shouting. We do not conquer distance, we learn its shape, and we learn what it does to plans. We do not break the universe, we listen to what it permits. The boundary is not a wall we will someday smash, it is the frame that makes the cosmos coherent. We began with our honest yardsticks, Voyager and New Horizons, still whispering home from a region that only feels distant to us. Then the layers revealed themselves one after another. Relativity's non-linear energy price, thermodynamics' waste heat receipts, and an interstellar medium that turns speed into radiation and shrapnel. Even if propulsion works on paper, the voyage becomes a closed world, where gravity, biology, microbiomes, materials, medicine, and meaning must remain stable for decades or centuries. And above all of it sits time itself. Institutions drift, crews become civilizations, and the cosmos keeps expanding, quietly tightening the map of what can ever be reached. That is why the unresolved questions never vanish. They only move deeper into the stack. How much rotation is enough gravity for children who have never walked under 1G, and can bearings, seals, and balance survive a lifetime without a supply chain? Can a sealed habitat keep its chemistry, ecology, and pathogens inside a safe basin? Or will small feedbacks eventually tip it into a new equilibrium that humans cannot inhabit? Can a mission preserve legitimacy across generations when consent becomes inheritance, and arrival is no longer a promise but a story told by ancestors? And even if all of that holds, the universe itself is not static, because horizons are not walls you hit. They are boundaries that slowly move inward as expansion stretches the future. Put those chapters together, and the shape of the barrier changes. It is not one impossibility, but an architecture of compounding costs, where every solution adds mass, heat, complexity, risk, and time, each payment demanding another. The nearer stars remain physically reachable in principle, yet the practical route passes through a narrowing corridor, where the ship must be a reactor, a fortress, a hospital, a library, and a government, all at once. Interstellar travel becomes less like crossing an ocean, and more like trying to carry an entire century intact without cracking. And that is before the quietest limit speaks. The light speed rule is not a speed limit like a sign on a road. It is the geometry of cause and effect, the shape of what can influence what. As the universe accelerates, it draws a faint line in space-time, an event horizon, past which even perfect messages launched forever never arrive. The night sky is not merely far, it is a set of timelines, and some of those timelines are slowly being removed from our future. So the real barrier is not a missing engine, or a single hostile hazard, or a lack of courage. It is that distance is enforced by causality, paid for in energy and entropy, and lived through by fragile bodies and unstable civilizations. The faster you try to make the trip, the more the medium fights back, the more heat you must dump, and the more mass you must carry to survive your own velocity. The slower you go, the more the mission becomes a long political experiment, where the destination can outlast the reason you left. Even the weight equation becomes part of the same geometry. Launch too early, and a later generation may pass you with better power, better shielding, and better medicine, turning your sacrifice into a historical footnote. Wait too long, and the horizon keeps doing its work, and the reachable universe grows smaller while your certainty grows older. The trap is not indecision, it is that progress and distance do not scale together, because the universe is not obligated to meet our timelines. In that sense, the ship's endgame is not a technical checkbox, it is a philosophical fork. If the culture aboard changes, if the habitat becomes home, then landing is no longer a victory condition. It is merely one option among many. A generation raised inside a rotating world may not see a planet as salvation, but as danger, or as exile, or as a myth that no longer fits their bodies. The mission's purpose can survive only if it can be translated, again and again, into a meaning that still persuades people who never chose the original bargain. And yet, none of this makes the universe smaller, or the dream less beautiful. It only clarifies what kind of dream it is. For humans, as we are built and as our societies behave, the stars are separated from us by an unbridgeable architecture of time, reinforced by energy curves, heat laws, and a thin, lethal dust between suns. Interstellar travel is allowed by physics, but made effectively impossible by the way the costs stack, and by the fact that we must pay them with lives. The practical future, then, looks less like migration and more like outreach, probes that do not need childhood, or consent, or bones that remodel under gravity, can accept journeys that humans cannot. AI emissaries, autonomous laboratories, beamed sails, and interstellar telescopes can turn distance into data and time into patience, letting knowledge arrive where bodies cannot. We may never be a species that walks under alien constellations, but we can still become a species that listens, measures, and understands, expanding across the solar system and outward through instruments that extend our senses. In the cold open, we asked what the real wall was: distance, time, energy, biology, or expansion itself, and why going to the stars feels like a locked cell. The answer is that the wall is not any single one of those, but their multiplication, because space-time is layered, and each layer demands a different currency. You can spend fuel, you can spend mass, you can spend complexity, you can even spend generations, but you cannot spend your way around causality, or bribe entropy, or negotiate with a horizon. The stars are not waiting for us, because waiting is a human verb, and the universe is not built on human time. If there is closure here, it is this. The barrier is real, and it is not a failure of imagination. It is a discovery about what kind of cosmos we inhabit. The night sky is not a promise of destinations. It is a record of light already on its way, crossing distances that our bodies cannot casually follow. And perhaps that is the final twist. Our most honest form of interstellar travel is not migration, but comprehension, because understanding can cross the gap without dragging a fragile civilization through it. So when you look up, remember what those points of light really are. They are not doors, they are clocks, each one telling you how time, not space, rules the map. And the most profound journey we can still take is to learn the universe so well that even from here, we can touch it with truth. If this story changed how you see the sky, keep going. Follow the data, support the telescopes, and ask better questions, because knowledge is the one vessel that does not need to outrun light. The real wall is the universe's layered structure of space-time, causality enforcing light speed limits, thermodynamics charging waste heat, the interstellar medium weaponizing velocity, and human biology and civilization unraveling under deep time. The stars are not unreachable in principle, but for humans they are separated by an architecture of time that no invention can cheat. The night sky is not a frontier waiting to be crossed. It is a tapestry of timelines, and some threads are already slipping beyond our future. We may never carry our bodies to the stars, yet we can still send our understanding and let it return, light years later, as proof we were here. So look up, then look deeper. Support the instruments and the science that turn impossible voyages into shared knowledge, and keep asking what the universe will and will not allow.